Greetings, and welcome to Echoes of the Forgotten Earth, a place where curiosity takes off its shoes and science wraps itself in a cozy comforter. In November 1969, something unfolded on the lunar surface that still fuels arguments more than half a century later. During the Apollo 12 mission, after the astronauts had rejoined the command module, NASA intentionally directed the ascent stage of the lunar module to crash back into the moon. When it slammed into the surface, the seismometers the crew had left behind recorded something nobody had anticipated. The moon rang. Not literally, of course, like a bell filling space with audible sound waves. Sound can't travel through a vacuum. But the seismic vibrations were unmistakable. The seismograph data showed that the entire body of the moon continued to vibrate for over 55 minutes. Engineers at NASA reached for a metaphor to describe it. The moon rang like a bell. That short phrase set off years of speculation, follow-up experiments, and a long tail of conspiracy theories that has never quite died. But what does it really mean for the moon to ring? To see why this was so unsettling, you have to understand how seismic events usually unfold. On Earth, when an earthquake strikes, the energy ripples through different layers of rock and molten material. As those waves move through our crust, mantle, and the outer and inner core, they speed up, slow down, bend, or get absorbed depending on the materials they encounter. Earth's interior is hot, active, and partially molten. That churning interior acts as a natural damper, soaking up and scattering seismic energy so that most quakes die away relatively quickly. On the moon, though, something very different occurred. Instead of fading quickly, the vibrations lingered. They kept bouncing through the lunar interior for nearly an hour, and they did so in an unusually uniform way. That kind of long-lasting reverberation hinted that the moon's insides were not behaving like those of a geologically active world. It acted more like a giant, dry, solid blocker in the most extreme interpretation, like a hollow shell. Hollow moon ideas, and why NASA at least had to check them. Saying the moon is hollow sounds straight out of pulp science fiction. And to be clear, no serious modern model of lunar formation supports a truly hollow interior. But at the time of the Apollo missions, the data were so odd that NASA scientists were forced to consider that the moon might have very unusual internal structures. Some early theoretical models allowed for a small or partially molten lunar core. Others pictured the moon as a completely solidified body. But this bell-like resonance seemed to suggest there wasn't much internal damping at all. No large molten core soaking up energy, and a crust that was astonishingly rigid and bone dry. As more Apollo missions delivered seismometers, the pattern held. Across multiple landing sites, the seismic experiments showed that moonquakes behave in ways unlike earthquakes on our planet. Lunar tremors persist longer, travel farther, and don't always line up with the familiar tectonic faults and plate boundaries that dominate Earth's seismic map. That raised an unnerving question. Could the moon actually be some kind of hollow shell? Almost certainly not. But its weird behavior forced geophysicists to rip up and redraw their picture of the moon's interior. The follow-up data only made things stranger. Apollo 13 never touched down on the moon, but it still added one of the most dramatic entries to this puzzle. In April 1970, mission controllers directed the Saturn IVB upper stage an empty rocket booster to crash into the moon. It hit with an energy equivalent to roughly 11 tons of TNT, and once again, the lunar seismometers captured what happened next. This time, the moon rang for more than 3 hours. 3 straight hours of measurable seismic activity. Certain frequencies kept going for more than 8 hours. The signals didn't just echo and fade chaotically. They built up and then slowly decayed in a pattern no one had predicted. The response was more like striking a massive crystal. Clear, sharp resonance, not shattered rock breaking and grinding itself into silence. Geophysicist Dr. Clive R. Neal would later remark, "The moon was ringing like a bell." The implications were deep, and the answers were not obvious. So what actually lies inside the moon? To move past the more exotic ideas, you have to look at what modern missions have revealed. Recent measurements, especially from NASA's GRAIL, Mission Gravity Recovery, and Interior Laboratory, have given us a much sharper view of the lunar interior. The moon, as we now understand it, has a relatively thin crust averaging about 50 kilometers thick, overlying a partially molten mantle with regions of different stiffness, and at its center a small solid inner core surrounded by a tiny liquid outer core, both far smaller in scale than Earth's equivalents. But there's a crucial twist. Compared to Earth, the moon is both extremely dry and lower in overall density. Those two facts radically change how seismic energy moves. Without vast reservoirs of liquid water and large pockets of molten rock to scatter and absorb vibrations, seismic waves inside the moon tend to travel farther and ring longer, producing that eerie bell-like effect. On top of that, the moon has no system of shifting tectonic plates. There are no subduction zones, no mid-ocean ridges, no constant crustal recycling like we see on Earth. Instead, the crust is cold, static, dense, and riddled with fractures carved by billions of years of meteorite and asteroid impacts. That means, when energy slams into the moon, whether from a natural moonquake or from the controlled crash of a spacecraft, it propagates through a rigid, echo-friendly structure. The moon isn't an empty shell. It's just dry, brittle, and surprisingly prone to ringing. Even so, the bell analogy refuses to fade. The image is too vivid, and the data that inspired it were too strange. The phrase has become a favorite talking point for skeptics and fringe thinkers who argue that the resonance proves the moon is artificial. Their ideas range from the moon being a vast alien outpost to an intentionally placed monitoring station to a starship cloaked in rock. There's no solid evidence supporting any of these claims. But that single ringing event has joined the catalog of space oddities like puzzling UFO reports or speculative faces on Mars that invite endless storytelling. And to be fair, the moon is odd in plenty of legitimate ways too. Its relative size compared to Earth, its locked rotation, its orbit, and its still uncertain origin story all raise deep questions. The ringing is just the first shallow crack in the facade of a mystery that goes far deeper. Why does any of this still matter? You might be tempted to shrug this off as a quirky footnote in the annals of space exploration, but the way the moon rings is not just a curiosity. It's one of the most important clues we have for deciphering how rocky worlds are built. Seismic waves are our only direct probe of a planetary body's hidden interior. On Earth, earthquakes revealed the existence and structure of our core and mantle. On the moon, moonquakes serve the same role. By studying how these vibrations travel, scientists can test whether the moon ever powered a dynamo like Earth's, generating a strong global magnetic field. They can refine models of the violent collisions and accretion processes that shaped the early solar system. They can figure out how stable the lunar crust really is when it comes to building bases, because any future lunar settlement has to be designed to withstand quakes that can rattle for minutes or hours. They can also map out buried structures, identify regions where water ice or certain minerals might be trapped beneath the surface, and generally turn the entire moon into a natural laboratory. Every time we record a moonquake or measure the seismic response to an impact, we peel back another layer of the moon's hidden anatomy. And sometimes, those lessons literally come in the form of echoing, bell-like resonances. Is the moon still ringing today? Not in the way it did when we deliberately crashed hardware into it, but the underlying enigma hasn't gone away. As humanity prepares to send crews back to the lunar surface under NASA's Artemis program, there are serious plans to deploy a new generation of seismometers with far better sensitivity and broader coverage than anything Apollo carried. This time, instead of a sparse network of instruments, we may create a real seismic grid. The moon almost certainly still trembles. Meteoroids still strike. Internal stresses still shift. And thermal cracking still snaps the crust. If we once again send large masses crashing into the surface, scientists will be listening closely for what follows. If the moon responds with that same drawn-out crystalline reverberation, we'll have even more data to help solve a riddle that began with a single, unforgettable phrase: the moon rang like a bell. No one knows how the moon got here, and every theory has problems. For an object that dominates our night sky and has shaped human culture since before recorded history, the moon remains astonishingly puzzling. You might expect that by now, planetary scientists would have settled on a single, well-tested origin story. They haven't. Instead, the question of how the moon formed is still one of the most hotly contested problems in planetary science. Every time a proposed solution looks promising, new measurements appear that tear holes in it. The uncomfortable truth is, we still don't know exactly where the moon came from. We have hypotheses, computer models, and elaborate simulations, but each candidate scenario runs into serious issues. And ironically, the more closely we examine lunar samples and orbital data, the stranger the puzzle becomes. The most widely taught explanation, the one that shows up in textbooks and science documentaries, is called the giant impact hypothesis. In this scenario, over 4 billion years ago, a Mars-sized protoplanet slammed into the young Earth. This intruder, often called Theia, struck with such violence that huge quantities of material from both bodies were blasted into orbit. That debris formed a ring around Earth, which eventually clumped together through gravity to become the moon. For a while, this dramatic cosmic collision seemed to neatly account for several key facts. The moon lacks a large, dense iron core, which fits with the idea that it formed mostly from the outer layers of Earth and Theia, not from their metallic centers. The moon's smaller size and its distance from Earth lined up with simulations, and computer models showed that a collision like this really could launch enough material into orbit to assemble a moon-sized object. But as often happens in science, the trouble started when the data got better. When the Apollo astronauts brought lunar rock samples back to Earth, geochemists compared their composition to terrestrial rocks. They expected to see clear differences reflecting the mixed heritage of Earth plus Theia. Instead, they found something unsettling. The moon rocks were almost indistinguishable from Earth's in their isotopic fingerprints. In particular, the oxygen isotopes in lunar samples matched Earth's almost perfectly. Ratios of other key elements like silicon and titanium were also eerily similar. If a significant portion of the moon's material came from a separate body that had formed elsewhere in the solar system, those isotopic patterns should have diverged. Planetary embryos that grow in different regions of the protoplanetary disk don't end up chemically identical. Yet the moon looks, chemically, like it is made almost entirely of Earth. That's the first major crack in the giant impact story. The chemistry doesn't really fit. In response, theorists modified the model. What if Theia just happened to have nearly the same isotopic composition as Earth? What if the impact was so energetic that the two bodies were completely vaporized and mixed, erasing any original differences before the moon condensed? What if Earth had been spinning much faster than assumed, flinging more of its own material into orbit? Each of these tweaks can be made to work on paper, but they raise new questions. How likely is it that two independent protoplanets formed in different orbital zones would share almost identical isotopic signatures? It's not impossible, but it strains probability. And even if thorough mixing did occur, why does the moon's composition so closely match Earth's mantle rather than some average blend of both bodies? Because of these issues, some researchers have revisited older alternatives. One is the co-formation, or co-accretion model. In that picture, Earth and the moon condensed side by side from the same patch of material orbiting the sun, more like planetary siblings than parent and child. That would naturally produce similar chemistry, since both objects would be made from the same ingredients. But this idea runs into dynamical problems. If Earth and the moon form together in this way, their present-day orbital relationship is hard to explain. The moon's mass, its distance, and its angular momentum don't match what you'd expect from two bodies that simply grew next to each other in the same disk. When you run the numbers, the orbital mechanics just don't cooperate. Then there's the capture hypothesis. In that scenario, the moon formed elsewhere in the solar system and later wandered into Earth's gravitational field. Under just the right conditions, Earth's gravity would have captured it into a stable orbit, instead of either flinging it back into space or pulling it into a destructive collision. This has some intuitive appeal, Many moons in the outer solar system probably are captured objects, and Earth's moon is oddly large compared to its host planet, which might hint at an unusual origin. But again, the physics push back. Capturing a body as massive as the moon into the near-circular, relatively stable orbit we see today is extraordinarily difficult without some third factor to dissipate energy. A thick atmosphere, a large companion, or a drag mechanism we have no evidence for. It's a bit like tossing a baseball out a car window and having it fall into a perfect orbit around a nearby lamppost. In theory, the math allows it. In practice, the odds are microscopic. Other, more exotic models have also been floated. Some suggest that instead of a single catastrophic impact, the moon could have formed from the combined debris of multiple smaller collisions over time. Others propose that Earth once had a whole family of smaller moons that gradually merged, leaving a single survivor. Still others envision a cloud of vapor and molten droplets coalescing around Earth in complex stages. These proposals can address some of the chemical or dynamical issues, but each one runs aground on some combination of constraints. They might match the isotopic data, but fail to reproduce the present-day orbit, or they might satisfy the orbital history while predicting a moon with the wrong internal structure. None of them so far nails everything at once. And then there are the coincidences that don't fit neatly into any theory. Consider the moon's apparent size in our sky. By sheer happenstance, the moon sits at just the right distance and has just the right diameter that it appears almost exactly the same size as the sun from Earth. That's why we get total solar eclipses in which the moon can cover the solar disk almost perfectly, revealing the delicate halo of the corona. The sun is about 400 times larger than the moon in diameter, but also about 400 times farther away. The ratio lines up so closely that the two bodies span nearly the same angle, about half a degree, when viewed from Earth. No other planet in our solar system enjoys anything quite like this. Many have moons. Some of those moons are bigger, some orbit closer, but none produce clean total eclipses as precisely as ours. Earth is the only world we know of where the sky can be darkened in that specific theatrical way. Some scientists are content to treat this as a statistical curiosity. In a universe of countless planetary systems, you'd expect some strange alignments just by chance. Others wonder whether these alignments hint at deeper selection effects or still unknown principles. On the fringes, people spin entire narratives out of this one coincidence, suggesting intention where mainstream science sees only probability. What complicates things further is that the configuration is temporary. The moon's orbit is not static. As tidal interactions between Earth and the moon slowly transfer angular momentum, the moon is creeping away from us at about 3.8 centimeters per year. Millions of years ago, it was closer and looked larger in the sky. In that era, solar eclipses would have been longer and more complete. Millions of years from now, it will be farther and too small to fully obscure the sun. Total eclipses will fade into annular rings and then disappear altogether. That means we happen to be living in a thin slice of geological time when the apparent sizes of the sun and moon are so finely matched that these perfect total eclipses can occur. Across billions of years of Earth's history, this window is narrow. The chance that conscious observers arise during precisely this era has struck more than a few thinkers as eerie. There are additional numerical curiosities. The moon's rotation period, 27.3 days, is the same as its orbital period around Earth, which is why it keeps the same face turned toward us. Its orbit is elliptical, so its apparent size varies slightly depending on whether it's at perigee, closest approach, or apogee, farthest point. And that variation leads to different kinds of eclipses: total, annular, hybrid. Even these changes follow long, repeating cycles. The Saros cycle, for example, about 18 years, 11 days, and 8 hours, governs the repetition of similar eclipses. Ancient astronomers noticed and predicted these patterns long before they understood any of the physics behind them. Modern celestial mechanics can model all of this behavior in exquisite detail. We can rewind and fast-forward the orbits, track how the tidal evolution alters distances and rotation rates, and project when the last total solar eclipse will occur. But what the equations don't answer is the philosophical why lurking behind the how. Why does our one large moon match the sun's apparent size so uncannily from our specific vantage point? Why did complex life and consciousness arise during the brief era when this match is exact enough to produce total eclipses? Most scientists chalk these questions up to anthropic selection effects. We notice the coincidences that happen in the universe in which we evolved, and we inevitably weave stories around them. A small minority speculate about deeper rules or unknown physical principles. And from the outer edges of speculation come claims that the moon's orbit and size are not the product of natural processes at all, but indicators of design, placement, or even artificial construction. Those ideas sit well outside mainstream science. There's no credible evidence that the moon is anything other than a natural object born of violent astrophysical processes, but they persist in the public imagination, in part because the numbers do feel so strangely precise. Even if you ignore the speculative edges, the reality itself is remarkable enough. The moon is uniquely positioned to create what may be the most dramatic celestial events visible from any inhabited world in our solar system. Total solar eclipses have shaped mythologies, terrified empires, inspired scientific revolutions, and, in the modern era, drawn millions of people to stand together under a suddenly darkened sky. And all of that, the culture, the fear, the wonder, is temporary. Every total eclipse you see is part of a countdown. In the distant future, when the moon is drifted farther out, no living creature will ever again stand on Earth and see the sun's face blotted out so precisely. They'll see partial coverages, rings of fire, or nothing at all. The moment we inhabit is special, whether you consider it coincidence, inevitability, or something in between. So while we argue about giant impacts, co-formation, captures, and mergers, one point stands firm. We do not yet have a fully satisfying, gap-free account of the moon's origin. The giant impact hypothesis remains the leading candidate, but its chemical and dynamical fine-tuning make many researchers uneasy. The more we sample lunar rocks, map its interior, and run high-resolution simulations, the more tangled the picture becomes. The moon hangs there, bright and steady, as if it were the simplest thing in the sky. But its birth story is still missing key pages, and that gap isn't just an isolated curiosity. It cuts to the heart of how planets, moons, and entire solar systems assemble. If we can't fully explain our own moon, the closest and best studied natural satellite we have, how confident can we really be in our broader theories of world building? The moon is moving away from us, and it's changing time. The moon feels eternal, a fixed part of the night sky, but it isn't fixed at all. It's slipping away. Every year, little by little, the moon drifts farther from Earth, and that slow retreat is quietly altering something fundamental: the length of our day. Right now, laser measurements show that the moon is receding at about 3.8 centimeters per year, roughly the speed at which human fingernails grow. That doesn't seem like much, but over geological timescales, it reshapes the entire Earth-Moon system. To understand what's happening, you have to look at tides, not just the waves lapping on beaches, but the gravitational choreography that produces them. The moon's gravity tugs on Earth's oceans, pulling water into bulges on the side facing the moon, and, less intuitively, on the opposite side as well. If Earth didn't spin, those bulges would point directly toward and away from the moon. But Earth does spin, and it spins faster than the moon orbits. A full rotation takes 24 hours, while the moon needs about 27.3 days to complete one lap. Because of that, the tidal bulges are dragged slightly ahead of the moon's position in its orbit. Those forward-leaning bulges exert a gravitational pull on the moon, giving it a tiny but constant forward kick. That transfers energy and angular momentum from Earth's rotation into the moon's orbit. The result is a perpetual trade. The moon slowly gains orbital energy and climbs into a higher orbit, moving farther away. At the same time, Earth loses a bit of its rotational energy and spins more slowly. That means days are gradually lengthening. Today, the change is small, about 1.7 milliseconds per century. You will never notice it within a human lifetime, But if you rewind the clock hundreds of millions of years, the effects become dramatic. Fossil corals, tidal sediment layers, and other geological records preserve ancient rhythms that betray the length of past days. Around 400 million years ago, during the Devonian period, a day on Earth was about 22 hours long. Go back about 1.4 billion years, and the day shrinks to roughly 18 hours. The Moon, in turn, was closer about 341,000 kilometers away on average, instead of today's roughly 380,400 kilometers. In those eras, the Moon would have loomed larger in the sky, and tides would have been stronger and more extreme, crashing further inland and pulling harder on coastlines. Today, thanks to laser retroreflectors left on the Moon by Apollo astronauts, we can measure this drift with astonishing precision. By firing laser pulses at these mirrors and timing how long it takes the light to return, scientists can track the Moon's distance down to the millimeter. Those observations confirm exactly what tidal theory predicts. The Moon is receding, and Earth is slowing. This subtle connection between orbital motion and the length of a day is one of the quietest but most powerful interactions in our local celestial neighborhood. It means the Moon is not just passively orbiting us, it is actively reshaping the tempo of our world. Our 24-hour day, our entire sense of daily time, is bound to this gravitational relationship. Project this into the future, and the consequences become even stranger. If nothing else interferes, no major changes in ocean geography, no catastrophic impacts, no significant external torques, then in the ultra-distant future, the Earth and Moon could reach a state of mutual tidal locking. In that configuration, one side of Earth would always face the Moon, just as one side of the Moon always faces Earth now. Earth's rotation period and the Moon's orbital period would match. A single day would last as long as a lunar month, by some estimates, around 47 of our current days. Under those conditions, one hemisphere of Earth would see the Moon permanently fixed in the same place in the sky, while the other hemisphere would never see it at all. The daily cycle as we know it, sunrise and sunset every 24 hours, would vanish. Light and darkness would follow a much slower rhythm, more like what tidally locked exoplanets may experience around their stars. Of course, this isn't something any future human civilization is likely to witness. The Sun will evolve first. In roughly 5 billion years, it will swell into a red giant, potentially engulfing or sterilizing Earth long before full mutual locking occurs. So this scenario lives mostly in the realm of theoretical celestial mechanics, but it illustrates an important truth. The system is not static. Time itself, as we measure it by planetary rotation, is fluid on cosmic scales. There's another wrinkle. Geological evidence suggests that the Moon's rate of recession hasn't always been smooth. Certain rock formations and fossil patterns hint at periods when tidal behavior changed more rapidly than simple models predict. That implies that the efficiency of tidal friction depends on the arrangement of continents, the depth and shape of ocean basins, and even glaciation cycles. As continents drift and collide, they reshape the oceans, which can enhance or diminish tidal dissipation. Ice ages that lock water into polar caps change sea levels and basin geometries. All of these factors modulate how effectively Earth transfers rotational energy to the Moon. In other words, Earth's geography may be influencing how quickly the Moon drifts away, which in turn affects how fast our days lengthen. It's a feedback loop connecting plate tectonics, climate, gravity, and time. The Moon's recession also matters for another reason: axial stability. Right now, Earth's axial tilt sits at about 23.5 degrees and varies only slightly over tens of thousands of years. That modest wobble is part of what drives ice age cycles, but it keeps our seasons within a relatively stable range. Without the Moon's stabilizing mass, models suggest that Earth's tilt could wander chaotically, swinging from near zero to over 60 degrees. In such a world, the poles could at times point almost directly at the Sun, baking under permanent daylight, while at other times they might sit in near permanent twilight. The equator could alternate between mild and icy extremes. Climate patterns would be far more erratic, and long-term habitability for complex life might be much less secure. The moon's presence and its slow outward journey are part of what has kept Earth's climate inhabitable over deep time. We owe our current 24-hour rhythm to the exact way this system has unfolded. The length of our day, the cadence of dawn and dusk, the stability of the seasons. These aren't arbitrary. They're products of a gravitational interaction that has been running since Earth and the moon first formed. The moon has been a silent timekeeper long before clocks, calendars, or humans existed. So the next time you glance up at the moon, remember that it is not fixed. It is leaving, slowly, invisibly, centimeter by centimeter. As it goes, it pulls on our oceans, tugs on our rotation, and stretches our days by fractions of a millisecond at a time. Over human lifespans, the change is negligible. Over geological epochs, it is rewriting the timeline of our planet. The moon is drifting. Time is bending with it. Even something as ordinary as the length of a day turns out to be a moving target, shaped by a companion we still sometimes mistake for a static light in the sky. The moon's size and distance are a mathematical coincidence, or not. There's something uncanny about watching a total solar eclipse. For a few fleeting minutes, the moon slips directly in front of the sun and covers it with startling precision. The solar disk disappears, the sky darkens, stars appear, yet a halo of ghostly light, the sun's corona still shines around the edges. The fit is so exact it feels engineered, as if the moon were designed to act as a perfectly sized cover. The underlying numbers make it even stranger. The sun's diameter is about 1.39 million kilometers. The moon's is about 3,474 kilometers. The ratio between them is roughly 400. Meanwhile, the average distance from Earth to the sun is about 149.6 million kilometers, and from Earth to the moon, about 384,400 kilometers. Divide those, and you again get a factor of about 400. The sun is roughly 400 times wider than the moon, and 400 times farther away, so the two appear almost exactly the same size in our sky about half a degree across. The match isn't perfect. Both orbits are slightly elliptical, so apparent sizes vary. Sometimes the moon looks a bit larger or smaller. That's why we see different flavors of eclipses. When the moon is close enough at the moment of alignment, we get a total eclipse, where it fully covers the solar disk. When it's slightly farther, its apparent size shrinks, and we see an annular eclipse, a ring of fire, where the sun's edge still peaks around the moon. But even with those variations, the correspondence is close enough to produce total eclipses that feel almost surgically precise. What are the odds that a planet would have a single large moon whose apparent size matches its star so well that it can produce these unique events? Within our solar system, Earth appears to be alone in this respect. Other planets have moons. Some of those moons are huge, but none give rise to clean total eclipses of their parent star the way ours does. Mars, for instance, has two tiny, irregularly shaped moons, Phobos and Deimos. They're too small to ever fully obscure the sun from the Martian surface. Giant planets like Jupiter and Saturn have many large moons, some larger than Mercury. But their moons' orbits and relative sizes don't create the same visual coincidence. Earth stands out. To mainstream astronomy, this is an interesting quirk, but not evidence of anything mystical. In a universe with untold numbers of planetary systems, you'd expect some improbable alignments simply because there are so many chances. We happen to live on one of the worlds where the geometry lines up this way. Still, the numerical neatness is hard to ignore, and it has long been a magnet for speculative thought. The weirdness doesn't stop there. The moon's orbit is slowly changing. Because of the tidal interactions that are pushing the moon away from Earth, its apparent size in our sky is gradually shrinking. Millions of years ago, the moon was closer and looked larger. In that era, total solar eclipses would have been deeper and longer. Millions of years in the future, it will be farther away, and even at its closest approach, it will be too small to fully cover the sun. Total eclipses will end. Only partial and annular events will remain. That means we exist in a narrow temporal window when the apparent sizes of the sun and moon are so finely tuned that these exact total eclipses can occur. Considering Earth's multi-billion-year history, this is a razor-thin slice of time. For eons before and after our era, any intelligent observer on Earth would see a very different sky. There are other rhythms embedded in the Earth-Moon-Sun geometry. Because the Moon's orbit is elliptical, its distance from Earth swings between perigee, closest point, and apogee, farthest point. That causes subtle changes in its apparent size. Overlay that with the tilt of Earth's axis and the inclination of the Moon's orbit, and you get evolving eclipse patterns that repeat in long cycles. One of the best known is the Saros cycle, about 18 years, 11 days, and 8 hours. After each Saros period, the Earth, Moon, and Sun return to nearly the same geometry, and a new eclipse very similar to the previous one occurs, shifted slightly in latitude and longitude. Ancient Babylonian astronomers discovered this cycle millennia ago by painstakingly recording eclipses and noticing the pattern long before they had any physical explanation for it. They saw order where others saw chaos. Modern celestial mechanics explains all of these relationships in terms of orbital periods, inclinations, and perturbations. We can calculate the Moon's distance and apparent size at any given time, reconstruct past eclipses, and predict future ones with exquisite accuracy. The math is clear, but math alone doesn't answer the deeper, almost unsettling question that lingers. Why should we find ourselves here and now, on this particular world, during the brief epoch when these alignments are so exact? Many scientists would argue that this is simply a case of the anthropic principle. We notice the universe as it is because we exist in it, not the other way around. Some go further, suggesting that phenomena like total solar eclipses may have played subtle roles in shaping human culture and science, giving early astronomers dramatic incentives to study the sky, refine calendars, and develop predictive models. Others wonder whether such coincidences might hint at unknown patterns in planetary formation or evolution we haven't fully uncovered. From the fringes come more radical ideas, that the Moon's orbit has been deliberately tuned, that it was placed rather than formed, that its matching of the Sun's apparent size is a signature of intent. These claims don't have empirical support and remain outside accepted science. But the power of the numbers, the double 400, the close angular sizes, the timing keeps them alive in popular imagination. Even if you set aside all speculation, the plain facts are striking enough. The Moon sits at just the right distance today to turn the Sun into a black disk edged with fire. It does this only for a limited span of Earth's long history. Those events have captivated humans for as long as we've been here to see them. They've been taken as omens, used as tools for political control, and later harnessed as natural experiments that helped scientists measure the Sun's corona, test general relativity, and probe the structure of the solar atmosphere. And when this window closes, when the Moon has drifted just far enough that totality is no longer possible, future observers, if any, will read about our eclipses the way we now read about ancient supercontinents, as features of a vanished era. They might find our photographs and simulations impressive, but they'll never experience the Sun disappearing behind a perfectly sized Moon with their own eyes. So when the sky darkens in daytime and the stars appear around a black Sun haloed in flame, you are witnessing a kind of mathematical miracle. Not in the sense of violating physical laws, but in the sense of an alignment so exact and so brief that it invites wonder. The Moon and Sun do not have to fit together like this. And yet, for now, they do. Parts of the Moon are older than Earth itself. It sounds backwards at first glance. How can something orbiting Earth be older than Earth's own crust? The Moon is usually framed as Earth's offspring, carved from it in a colossal impact or born from the same primordial disk. Yet locked in the Moon's rocks are clues that some of its material predates the solidification of Earth's surface, and possibly even carries fragments of other long-lost worlds. When Apollo astronauts first returned with lunar samples in the late 1960s and early 1970s, scientists expected ages comparable to Earth's oldest rocks, maybe slightly younger, depending on which formation scenario was right. Instead, dating the samples with radiometric methods revealed something extraordinary. Among the most ancient lunar rocks are anorthosites, bright, calcium-rich plagioclase rocks that make up much of the moon's highlands. These are the pale regions you see with the naked eye, contrasting with the darker basaltic seas. Measurements showed that some of these anorthosites formed about 4.46 billion years ago, only a few tens of millions of years younger than the estimated age of the solar system itself. That's remarkable on its own. It implies that the moon's crust began forming while the young solar system was still thick with dust, gas, and colliding planetesimals. But the comparison with Earth is even more striking. The oldest reliably dated rocks on Earth's surface are about 4.03 billion years old. There are individual zircon crystals that are older, up to around 4.4 billion years, but intact rock formations from that era are almost entirely gone. The reason is simple. Earth is geologically active. Plate tectonics, erosion, volcanism, and the constant recycling of crust have erased most of its earliest surface. The moon, in contrast, has no plate tectonics, no wind, no rain, and only the slow gardening of meteoroid impacts. Once a rock forms there and survives bombardment, it can sit in place for billions of years, a frozen snapshot from the deep past. Even with that in mind, the story gets stranger. Tiny zircon crystals, durable mineral timekeepers found within some lunar samples and in meteorites traced back to the moon, have yielded ages around 451 billion years. That pushes them back to a time before Earth's first stable crust formed. In some interpretations, these zircons may even predate the assembly of the moon itself. They could be relics from earlier planetary bodies that were shredded and incorporated into the material that later became the moon. If that's true, then parts of the moon are not just older than Earth's surface. They may be older than the final version of Earth as a planet. The moon, in this view, is a graveyard and archive, built from the debris of prior worlds. This places new pressure on our models of the moon's birth. The standard giant impact hypothesis posits that a Mars-sized body collided with the proto-Earth about 4.5 billion years ago, and that the moon condensed from the resulting disk of vaporized rock. For a long time, that event was imagined as a complete reset, a catastrophic obliteration followed by reassembly. But ancient zircons and old crustal ages complicate that picture. Did some solid material manage to survive the inferno of the impact? Were these grains and rocks embedded into the moon as it formed? Or did they originate from Theia, the impactor itself fragments of a lost planet whose remains we now walk on whenever we step onto the lunar surface? Recent refinements of impact models suggest that the collision that formed the moon may not have been a simple, single blast. Some scenarios envision a more complex series of interactions, or a less destructive glancing blow that left parts of the proto-Earth and Theia partially intact. In those cases, already differentiated crust and mantle material, along with any zircons they contained, could have been lofted into orbit and later welded into the growing moon. There's another provocative possibility. Some models propose that Theia may have formed closer to the Sun than Earth and migrated outward, or that it was a fully developed planetary embryo with its own crust and internal evolution. If Theia cooled and differentiated earlier than Earth, then its rocks would indeed be older. The moon, infused with Theia's material, would inherit that older timeline. In that sense, the moon could be thought of as Earth's older sibling, disguised as its satellite. A hybrid body containing the fossilized remains of a world that no longer exists. Where these ancient rocks are found on the moon strengthens this story. Most of the oldest samples come from the lunar highlands, the bright, heavily cratered uplands that ring the dark Maria. These highlands are believed to be remnants of the moon's original crust, formed when a global magma ocean, an entire moon's worth of molten rock, slowly cooled and crystallized. In that early epoch, lighter minerals like plagioclase floated upward and solidified into a crust, while heavier minerals sank into the interior. The highlands are the frozen top layer of that process. The anorthosites and zircons found there are essentially the first solid pieces of the moon to emerge from its primordial melt. They have been battered and excavated by impacts, but in many cases, not destroyed. Chemically, these rocks are distinct. They are extremely dry, lacking hydrated minerals common on Earth. They show signs of having formed in a vacuum under intense heat with no protective atmosphere. They preserve textures and compositions that record a time when the young solar system was a violent shooting gallery. Each micro-fracture and inclusion captures a moment from that chaos. Lunar meteorites, pieces of the moon blasted off by later impacts and eventually landing on Earth, tell a similar story. Some contain clasts that were melted and shocked by ancient collisions, hinting at impacts that occurred before the Earth-Moon system fully settled into its current configuration. These rocks have traveled twice, once from their original formation site to the Moon, and again from the Moon to Earth. They are geological refugees carrying layered histories. It's a strange realization. The Moon, which we habitually think of as Earth's child, may actually preserve more of the solar system's infancy than our own planet does. Under its gray dust and scarred plains lie materials older than any mountain, continent, or ocean on Earth. When we stand on the Moon, we are standing on the remnants of an era our planet can no longer remember. The more closely we examine those remnants, the more they remind us that Earth is not the beginning of the story. Our world is one chapter in a much longer narrative of collisions, mergers, destructions, and rebirths. The Moon is holding some of the earliest pages rocks older than any earthly landscape. Minerals forged before Earth's crust cooled, clues to worlds that formed and died before our own began. The Moon has a tail, and it passes over Earth. The Moon, from a distance, seems like the very picture of stillness, a pale, airless globe orbiting in silence. But in reality, it's shedding material into space all the time, and it even has a tail, a long, thin stream of atoms that trails behind it like a ghostly comet. And once each month, Earth passes right through this invisible plume. This isn't metaphor. It's a measurable physical structure, composed mainly of sodium atoms that have been blasted off the lunar surface and pushed into a vast, diffuse cloud by sunlight. The existence of this tail was first hinted at in the late 1990s, when astronomers using sensitive spectrometers detected a faint glow of sodium light associated with the Moon, especially near the new moon phase. Sodium atoms, when excited by energy, emit light at a specific yellow-orange wavelength, the same hue seen in some types of street lamps. Researchers noticed that this sodium emission wasn't confined to the immediate vicinity of the lunar disk. Under certain conditions, it seemed to stretch out into a long feature extending away from the sun. When they mapped the observations, a picture emerged. The Moon was trailing a comet-like tail of sodium tens or even hundreds of thousands of kilometers long. The process that creates it starts small. The Moon's surface is constantly bombarded by micrometeoroids, tiny grains of rock and dust hurtling through space at high speed. Without an atmosphere to slow or burn them up, they hit bare rock directly, releasing bursts of energy that vaporize minute amounts of the surface. Individual atoms, including sodium, are knocked free and thrown into ballistic trajectories above the Moon. At the same time, the solar wind and solar ultraviolet radiation strike the lunar surface, sputtering atoms off the regolith and into space. Sodium, being relatively light and volatile, is particularly susceptible. Once these atoms are liberated, they feel the pressure of sunlight itself. Photons carry momentum, and when they stream past sodium atoms, they impart tiny pushes. Over vast distances and long durations, those pushes add up. The sodium gets herded into a long, narrow tail that always points away from the sun, just like a comet's ion tail. During the new moon phase, when the Moon lies roughly between Earth and the sun, the geometry lines up so that Earth passes through the densest part of this sodium stream. For a brief period, our planet is bathed in a drizzle of lunar atoms. We don't see it. We don't feel it. But specialized instruments do. Telescopes equipped with sodium-sensitive filters can detect the glow of this tail as a dim, elongated patch of light stretching across the sky opposite the sun. It's extraordinarily faint, far below the threshold of human vision, but to the right detectors, it's unmistakable. In 2006, NASA's Messenger spacecraft, on its way to orbit Mercury, turned its instruments toward the Moon and confirmed the presence of this extensive tail, measuring it out to distances of more than 600,000 kilometers. That's over 1.5 times the distance between Earth and the Moon. The structure isn't dense by any normal standard. Space remains nearly empty, but it's coherent, persistent, and surprisingly large. The tail doesn't have noticeable effects on Earth. It doesn't change our atmosphere, alter our weather, or interact strongly with our magnetic field. It's so dilute that even as we pass through it, we remain oblivious. But its existence tells us something important. The moon is not inert. It's constantly interacting with its environment, losing particles to space, forming a tenuous exosphere, and responding to both solar and meteoritic forces. Sodium isn't the only element involved. The moon hosts an ultra-thin exosphere made up of helium, argon, neon, potassium, and traces of other gases. Many of them are produced by the same processes: micrometeoroid impacts, solar wind sputtering, and radioactive decay in the lunar interior. Together, they form a shifting, near-vacuum envelope around the moon that blurs the line between no atmosphere and the thinnest possible one. The sodium tail itself is not static. It strengthens during periods of increased micrometeoroid activity, such as when Earth and the moon pass through dense streams of cometary debris like the Leonid meteor shower. More impacts mean more vaporized sodium, which means a brighter, longer tail. Solar activity also plays a role. During times of intense solar radiation or heightened solar wind, more particles can be knocked loose and accelerated. In that sense, the tail is a kind of lunar weather vane, an indicator of how the moon is responding to its cosmic environment at any given time. It breathes with the flux of impacts and solar energy, waxing and waning in brightness and extent across the lunar month. All of this changes how we picture our nearest neighbor. The moon isn't just a static ball of rock. It's a dynamic, constantly eroding surface that quietly sprays atoms into space, and we live within reach of that spray. Once a month, whether we're aware of it or not, Earth drifts through the moon's faint exhalation. It's an almost poetic image. Our planet, massive and blue, crossing through an invisible, sunlit ribbon of sodium atoms shed from a gray, airless world. The breeze is too thin to feel. The light is too faint to see. But it's there, a subtle reminder that even seemingly dead worlds are embedded in a web of interactions richer and more active than they appear at first glance. The moon has quakes, some strong enough to damage bases. We tend to think of the moon as frozen in every sense of the word. No weather, no plate tectonics, no oceans, no storms. A place where nothing moves unless something crashes into it. That illusion made the moon seem like the ideal stable platform for instruments and, eventually, habitats. But beneath the quiet, cratered surface, the moon is not completely still. It shakes. It quakes. And some of those quakes are powerful enough to pose a real threat to future human structures. During the Apollo missions, astronauts didn't just bring back rocks and plant flags. They also set up seismometers, sensitive instruments designed to detect vibrations inside the moon. Over several years of operation, these devices recorded thousands of distinct seismic events. What they revealed overturned the assumption of a geologically dead world. Scientists now classify lunar quakes into 4 main types, each with different origins and characteristics. The first are deep moonquakes. These occur roughly 700 to 1,200 kilometers below the surface, deep within the moon's interior. They happen regularly and appear to be triggered by tidal stresses. As Earth's gravity tugs on the moon, it flexes slightly, building up and releasing stress in repeating patterns. These deep quakes are small to moderate in magnitude but remarkably consistent, clustering at certain points in the lunar orbit. The second category, shallow moonquakes, is far more concerning from an engineering standpoint. These occur only tens of kilometers beneath the surface and can reach magnitudes of around 5.5 on the Richter scale. On Earth, that would be a moderate quake. On the moon, with its rigid, dry crust and lack of damping materials like water and thick sediments, the energy propagates very differently. A shallow lunar quake of that strength can cause the ground to vibrate for many minutes, with little natural attenuation. Between 1969 and 1977, the Apollo network recorded 28 shallow quakes strong enough to be picked up across large distances. Some of them lasted longer than 10 minutes. That's critical. On Earth, most strong shaking is over in tens of seconds. On the Moon, it's more like striking a tuning fork. Once the vibrations start, they bounce around for an extended period. The third type are thermal moonquakes. These happen near the surface and are driven by temperature extremes. Because the Moon has no atmosphere, its surface undergoes brutal thermal cycling. During lunar day, temperatures can climb to about 127 degrees. At night, they can plunge to around 173 degrees. That's a swing of more than 300 degrees every lunar day-night cycle. As sunlight creeps across the surface at lunar sunrise, rocks and regolith heat up and expand. At sunset, they cool and contract. This repeated expansion and contraction can cause cracking, popping, and small shifts. Tiny quakes that constantly tick through the upper crust. Individually, you wouldn't feel them in a spacesuit, but they're a reminder that even in stillness, the lunar surface is constantly adjusting. The fourth type are impact-induced quakes. When meteoroids hit the Moon, and they do, frequently, they send shock waves through the crust. Without an atmosphere to burn up incoming debris, even relatively small rocks can hit hard enough to generate measurable seismic signals. Large impacts can send energy reverberating across much of the Moon. All of this adds up to a serious design challenge for anyone planning to build on the lunar surface. Future bases, whether from NASA's Artemis program, China's Chang'e series, or commercial outfits, will have to endure long periods of shaking in an environment where nothing softens the blow. Structures can't just be stable. They have to be resilient to prolonged vibration on brittle ground. Foundations will need to anchor securely in regolith that is loose, abrasive, and uneven. Habitats must absorb and redistribute energy without cracking seals, detaching modules, or damaging life support systems. Power lines, antennas, scientific instruments, and storage tanks all have to tolerate jolts. The fact that some shallow quakes occur in regions attractive for exploration, like near the lunar South Pole where ice may reside, complicates planning further. One of the biggest problems is that we don't yet have a global seismic monitoring network on the Moon. The Apollo instruments were clustered on the near side and operated only for a limited period. Their data have been reanalyzed with modern techniques, revealing even more complexity than originally recognized. But they can't tell us where quakes are most likely in the future, or how local geology affects shaking intensity. In 2019, researchers using old Apollo data in combination with images from the Lunar Reconnaissance Orbiter noticed a suggestive link. At least one recorded shallow moonquake appeared to originate near a recently identified fault scarp, a small cliff formed by crustal compression. That implies the Moon's crust is still slowly contracting and cracking as its interior cools, producing active faults and continuing seismicity. If that's representative, then the Moon is not just a relic. It's still adjusting and settling on geologic timescales. We'll be building bases on a world that, while far quieter than Earth, still moves unexpectedly from time to time. Any long-term presence has to accept that reality. So the next time you look at the Moon and imagine a tranquil, unmoving landscape, remember that deep below its silent face, stresses still build and release. And someday, when people are living and working there, they'll feel that motion, not as an abstract graph from Apollo days, but as a gentle or not so gentle shudder under their feet. Its dark side isn't actually dark. It's just hidden few phrases in astronomy are as misleading and stubborn as the dark side of the Moon. It's embedded in language, art, and popular culture. It evokes an image of a permanently black, mysterious hemisphere, cloaked from both sunlight and our view. But there is no permanently dark side of the Moon. There is a far side, a hemisphere we can't see from Earth without spacecraft, but it gets just as much sunlight as the side that faces us. The confusion comes down to how the Moon moves. The Moon is tidally locked to Earth. That means it rotates on its axis once every 27.3 days, the same amount of time it takes to orbit Earth. Because its spin and orbital period are synchronized, the same lunar hemisphere always faces our planet. If you stand on Earth and watch the moon night after night, you see the same large-scale pattern of Maria and Highlands with only slight apparent wobbling called libration, revealing a little extra around the edges. From our vantage point, the far side is never fully visible. Before the space age, no telescope on Earth could see it. That led people to imagine it as a realm of literal darkness. In reality, as the moon orbits, day and night sweep across its entire surface. When the near side is lit by the sun, what we see is a full moon. The far side is in night. 2 weeks later, when we see a new moon, the near side is dark. The far side is experiencing full sun. Over a lunar month, every point on the surface, except in permanently shadowed polar craters, cycles through day and night. The far side spends half its time bathed in sunlight and half in darkness, just like the near side. It's only dark from our perspective because we never see it lit. The first real look at the far side came in 1959, when the Soviet spacecraft Luna 3 sent back grainy black and white images. What they revealed shocked astronomers. The far side's appearance is dramatically different. It's dominated by bright, heavily cratered highlands with almost no large, dark Maria like the ones we see on the near side. The familiar face of the moon, with its broad basalt plains, does not exist there. On Earth's side, ancient asteroid impacts created huge basins. Later, volcanic eruptions filled many of those basins with dark basaltic lava, forming the seas of tranquility, serenity, and so on. On the far side, basins are fewer, and the crust appears thicker. That thicker crust may have prevented magma from breaking through and pooling on the surface, leaving the highlands exposed and cratered. Why the asymmetry? Several hypotheses compete. One suggests that when the moon was still molten, Earth's nearby presence radiated heat onto the facing hemisphere, altering how the crust formed and thickened. Another involves compositional differences in the mantle underneath each side. Whatever the cause, the result is a two-faced world. One side smoother and darker, the other rougher and brighter. Since Luna 3, multiple missions have mapped the far side in high resolution. NASA's Lunar Reconnaissance Orbiter has imaged nearly every crater and ridge. Gravity mapping by GRAIL has revealed subsurface structures there. China's Chang'e 4 mission made history in 2019 by soft landing a lander and rover U-2-2 on the far side, inside the von Karman crater within the vast South Pole Aitken Basin. Because direct radio contact with the far side is blocked by the moon itself, the mission relied on a relay satellite positioned beyond the moon to bounce signals back to Earth. That mission underscored a key reality. The far side is challenging, not unreachable. It's not a realm of permanent night. It's a place that simply doesn't face us, hidden by orbital mechanics and our own line of sight. And precisely because it's shielded from Earth's radio noise and has such ancient, undisturbed terrain, it's scientifically and practically valuable. Radio astronomers dream of placing telescopes on the far side, where Earth's chatter can't interfere. Planetary geologists want to sample its crust to understand why it's so different from the near side. Engineers and planners imagine future bases there, perhaps nestled in craters that never see Earth at all. Yet the phrase dark side of the moon persists, partly because it taps into something deeper. Humans are drawn to unseen places. We instinctively project mystery and danger onto regions beyond our view. For most of our history, half the moon was the ultimate unseen place. A hemisphere that never turned toward us, never changed in our sky. It became a canvas for speculation. Alien bases, secret structures, conspiracies hiding just out of sight. In reality, the far side is not hiding anything supernatural. It's hiding something arguably more fascinating. An ancient, heavily cratered record of the early solar system, a different face of the same familiar world, and a natural laboratory for science we can't easily do anywhere else. So it's time to retire the myth. The moon's far side is not truly dark. It's not a forbidden, lightless realm. It's a sunlit landscape that happens to be turned away from us by a gravitational lock billions of years in the making. Thanks to modern spacecraft, we've seen it in detail, landed on it, and started to treat it not as a shadowy mystery, but as the next frontier. There are patches of rust on the moon. Despite no water or oxygen on Earth, rust is a familiar and very terrestrial phenomenon. Iron plus water plus oxygen equals rust. Reddish iron oxides flaking off bridges, corroding tools, and staining rocks. It's such a basic reaction that we instinctively tie it to our own planet's damp, oxygen-rich environment. The moon, by contrast, is airless, dry, and bathed in vacuum. It has no liquid water, no breathable oxygen, and a surface scorched by unfiltered sunlight. Rust shouldn't exist there, and yet it does. In 2020, scientists analyzing data from India's Chandrayaan-1 mission stumbled on something unexpected. The spacecraft carried a NASA-built instrument called the Moon Mineralogy Mapper, M3, designed to map the composition of the lunar surface by measuring how it reflects different wavelengths of light. When researchers combed through its spectral data, they found signatures that looked very much like hematite, a specific form of iron oxide, Fe2O3. In other words, rust. At first, they assumed an error. Perhaps they were misreading the data, or the signal was contaminated. But as they checked multiple regions, viewing angles, and conditions, the hematite signature appeared repeatedly. It was most prominent at higher latitudes near the poles and especially on the far side of the moon. Hematite requires oxidizing conditions to form. On Earth, that usually means iron interacting over time with water and oxygen. The moon, on the face of it, provides neither in meaningful amounts. Its surface is baked dry. Its tenuous exosphere contains no significant free oxygen. So where was the oxidizing agent coming from? One intriguing answer points back to Earth. Our planet is surrounded by a magnetic field that deflects much of the solar wind. On the night side, that field stretches out into a long structure called the magnetotail. Earth's upper atmosphere slowly leaks atoms, including oxygen, into space. Some of those oxygen ions are trapped and channeled along the magnetic field lines into the magnetotail, extending far beyond our planet. Once a month, near full moon, the moon passes through Earth's magnetotail. During that time, it is partly shielded from direct solar wind and briefly exposed to a drizzle of oxygen ions originating from Earth's atmosphere. The idea is that over billions of years, this thin, intermittent stream of oxygen could have interacted with iron-bearing minerals in the lunar soil, especially in regions where trace amounts of water or hydroxyl exist. We now know, from multiple missions, that tiny quantities of water and hydroxyl groups are present in lunar regolith, particularly at higher latitudes and in shadowed regions. Solar wind protons can react with oxygen in the surface minerals to form hydroxyl. In permanently shadowed polar craters, actual water ice accumulates. Even outside those deep traps, molecules may hop and migrate with the temperature cycle. Combine that with occasional infusions of Earth-sourced oxygen, and you get a plausible, if slow, recipe for rust. Iron in the lunar soil, an intermittent oxidizer, trace moisture over immense timescales. You could form thin patches of hematite on exposed rock. There's another twist. The hematite appears to be more abundant on the far side of the moon than on the near side. That seems counterintuitive at first, since the near side faces Earth and might be expected to receive more of our escaping oxygen. But the near side is also more exposed to direct solar wind bombardment. The solar wind is rich in hydrogen, a reducing agent that tends to strip oxygen from iron, working against oxidation. On the far side, especially during magnetotail passages when the moon is shielded from direct solar wind, Earth's oxygen may have a better chance of reacting and staying in place, allowing rust to persist. The far side may thus offer a more favorable balance between oxidizing and reducing conditions, just enough oxygen, not too much hydrogen. If this picture is correct, it means the moon's surface chemistry is more dynamic and more intimately connected to Earth than we assumed. Our atmosphere doesn't end at the edge of space. It has a faint, extended influence that reaches all the way to our satellite, literally changing its rocks. From a practical standpoint, the discovery of hematite matters for another reason. Its presence can act as a tracer for where water or hydroxyl might be more concentrated in the regolith vital information for future explorers looking for in situ resources. Mapping rust could help identify spots where water chemistry has been active over long periods, even if the current water content is low. There's a strange irony in all this. Rust on Earth is usually an emblem of decay and neglect, bridges crumbling, ships corroding, tools falling apart. On the Moon, the same process becomes a subtle sign of connection and possibility. It hints at hidden water, at chemical pathways that defy our expectations, at a lunar surface still undergoing slow transformations under the combined influence of micrometeoroids, solar wind, and a distant but persistent halo of terrestrial oxygen. So yes, there are patches of rust on the Moon, clinging to rocks in a place that should be too dry and too airless for rust to exist at all. It's one more reminder that even in the harshest environments, chemistry finds a way, and that the boundary between Earth and Moon is more porous in some respects than empty space would suggest. The Moon might have an underground lava tunnel network. We usually picture the Moon as solid all the way through, a dense, unbroken ball of rock under a thin layer of dust. But the more we study its surface, the more it looks like there might be hidden hollow spaces below. Not artificial caverns or alien bases, but natural tunnels carved long ago by flowing lava. Evidence is mounting that the Moon once hosted enormous lava tubes, and some of them may still be intact, potentially stretching for miles. To see how that could be, you have to rewind the lunar clock billions of years. The Moon we see today is geologically quiet, but it wasn't always. Between roughly 3 and 4 billion years ago, the Moon was volcanically active. Huge volumes of molten rock seeped and spewed across its surface, flooding low basins and impact craters. Those ancient flows cooled into the dark basalt plains we now call Maria, the lunar seas. Lava doesn't only move on the surface, though. On Earth, in volcanic regions like Hawaii and Iceland, some lava flows develop insulating crusts while they're still active. The outer layer cools and hardens, forming a solid roof, while molten lava continues to move through channels underneath. When the eruption ends and the lava drains away, what's left behind is a hollow tube, a long cave-like tunnel, often with smooth floors and arched ceilings. Some terrestrial lava tubes are large enough to drive vehicles through or fit entire buildings inside. On the Moon, the same process likely took place, but under lower gravity and with no atmosphere or weather to erode the structures afterward. That means lunar lava tubes could be much larger and better preserved than anything on Earth. What's the evidence? One key clue comes from skylights, round holes observed in the lunar surface that appear to drop into subsurface voids. High-resolution images from NASA's Lunar Reconnaissance Orbiter have revealed multiple skylights in regions known to be ancient volcanic plains, such as the Marius Hills area and parts of Mare Tranquillitatis. These openings are nearly circular, with steep walls and flat floors visible in shadow, and they don't resemble typical impact craters. They look instead like collapsed ceilings. The most straightforward interpretation is that the skylights formed where the roof of a lava tube gave way, exposing the empty tunnel below. In some images, the surrounding terrain shows subtle linear depressions, hinting at the course of a buried tube stretching away from the skylight. Based on gravity measurements, surface collapse patterns, and comparisons with terrestrial geology, some scientists estimate that lunar lava tubes could be truly enormous, hundreds of meters to as much as 1,000 meters wide in some cases. The Moon's weaker gravity would allow such large voids to remain structurally stable without collapsing, especially if the rock making up their walls is strong basalt. If these tubes are as extensive as models suggest, they would be more than geological curiosities. They could be natural shelters for future human outposts. The lunar surface is a punishing environment. Unfiltered solar and cosmic radiation, constant micrometeoroid bombardment, and temperature swings of hundreds of degrees between day and night. Building habitats on the surface means contending with all of that. Inside a lava tube, many of those problems ease. The rock overhead would act as thick shielding against radiation and impacts. Temperatures deep inside would be far more stable than outside. dust, which is sharp and clingy and notorious for damaging equipment, would be easier to manage in enclosed spaces. Rather than constructing heavily armored bunkers on the surface, we could potentially seal and pressurize sections of existing lunar caves. Space agencies and researchers have started to take this idea seriously. Japanese data from the Selene Kagoya mission, for instance, identified what appears to be a particularly large potential lava tube under the Marius Hills region. Follow-up gravitational studies suggest an extensive subsurface void there. Concept studies from NASA, ESA, and other groups imagine future astronauts exploring, mapping, and eventually inhabiting these tubes, with habitats built inside long, protected corridors. Beyond habitability, lava tubes offer scientific opportunities. Because they've been sealed off from the surface for billions of years, they might contain well-preserved records of early volcanic activity, trapped gases, or even pockets of water ice. Their walls could preserve layering and textures that surface exposure would have erased. Exploring them would be like walking into a time capsule of the moon's hot, formative period. On Earth, lava tubes can interconnect into networks branching, merging, and stretching for many kilometers. If something similar happened on the moon, its underground might be crisscrossed by an entire system of tunnels beneath the Maria, currently invisible except where rare skylights open through. So far, no rover or lander has actually entered one. We don't yet know how stable they are, how far they extend, or what surprises they hold. Future missions may change that. Robotic explorers designed to rappel into skylights, hop across floors, and operate without GPS or sunlight are being proposed. Concepts include spider-like robots, tethered probes, and autonomous drones specially adapted for low-gravity caves. If they succeed, humans may eventually follow, becoming the first creatures to walk inside chambers that have been dark and untouched for more than 3 billion years. Imagine descending into such a tunnel, a vast arched ceiling fading into blackness, walls carved by ancient lava, silence absolute. No wind, no life, no sound, just the memory of a world that once flowed with fire. These lava tubes are not myth. They're likely real, waiting, hidden just beneath the gray plains we've stared at for ages. Apollo astronauts saw flashes of light on the moon. The moon's surface looks static and unchanging, but astronauts who visited it reported moments that didn't fit that picture. While orbiting or working near the lunar surface, some Apollo astronauts saw fleeting flashes, brief glints, glows, or pulses of light that seemed to come from the moon itself. They weren't alone. For centuries before Apollo, observers on Earth had reported strange lights on the moon through telescopes. Today, these events are grouped under a deliberately vague label: transient lunar phenomena, or TLPs. Take Apollo 11. While Michael Collins orbited the moon alone in the command module, he reported seeing an odd brief reflection or glimmer near the surface, something he didn't expect. On other missions, astronauts described quick, localized brightenings like tiny sparks or hazy patches that flared and faded. These events were rare, irregular, and hard to pin down, but they matched centuries of ground-based reports. Early documented sightings date back at least to the 18th century. William Herschel, the astronomer who discovered Uranus, claimed to see bright points of light on the moon that he interpreted, at the time, as possible volcanic eruptions. Over the years, amateur and professional astronomers alike recorded sudden flashes, mists, and color changes, especially in certain regions like the Aristarchus Plateau, the crater Plato, and others. TLPs fall into several visual categories. Some are point-like flashes, like a star winking on and off. Others are diffuse glows, sometimes with a slight color, pinkish, bluish, or white, that linger for seconds to minutes. A few reports describe hazy clouds that brighten and dim over a small area. They don't follow predictable patterns, which makes them notoriously hard to study. Skeptics long attributed TLPs to atmospheric turbulence, optical illusions, or observer-biased humans seeing patterns where none exist. Certainly, viewing a bright object like the moon through thick, unstable air can create all kinds of visual artifacts. But that explanation falters when similar phenomena are reported from above the atmosphere by astronauts and by instruments outside Earth's air. So what could be causing them? Several mechanisms have been proposed. One possibility is gas release. Although the moon is mostly inert, it isn't perfectly sealed. There is evidence of occasional outgassing tiny amounts of gases like radon or argon escaping from pockets within the crust. When micrometeoroids hit or moonquakes jolt the surface, they might open fissures that briefly vent gas. Under the right conditions, sunlight interacting with this gas or dust could produce a transient glow. Another candidate is electrostatic activity. The lunar surface is coated with fine dust that can become electrostatically charged by solar ultraviolet radiation and the solar wind. At the boundary between day and night, the terminator, changing illumination may cause charge imbalances that lift dust off the surface or discharge suddenly. These effects could, in theory, create faint flashes or halos of scattered light. Impact flashes are a more straightforward source. Telescopes have directly observed bright, short-lived flashes on the moon that clearly correlate with incoming meteoroids striking the surface. When a high-speed object slams into bare rock, it releases kinetic energy as heat and light, producing a tiny explosion. NASA and other groups now routinely monitor the moon for such flashes, especially during meteor showers. Many are too faint to see without specialized cameras, but occasionally a larger impact can be visible to an attentive observer. Even so, impact flashes don't easily explain some of the more diffuse, long-lasting TLPs people have reported, nor their apparent concentration in specific regions like Aristarchus, a bright, geologically intriguing crater complex with unusual reflectivity and suspected past outgassing. In recent years, interest in TLPs has been revived by better monitoring technology. Automated telescopes can now stare at the moon for hours, capturing high frame rate video and flagging any pixel-level changes. One project in Spain, for instance, is dedicated to capturing TLPs with robotic cameras. Many of the events it detects are almost certainly meteoroid impacts. Others are still being analyzed. Meanwhile, orbital spacecraft have found evidence that the moon is not completely geologically dead. Fault-scarped small cliffs formed by contraction of the crust suggest that the moon is still slowly shrinking as its interior cools. Some of these faults coincide with areas where moonquakes have been detected. It's not far-fetched to imagine that occasional stress releases, perhaps accompanied by minor outgassing and dust motion, could produce transient optical effects. For now, TLPs remain partly mysterious. No single explanation covers every report. Some sightings were likely illusions. Others almost certainly were real luminous events tied to impacts or subtle geological activity. What's clear is that the moon, while quiet on human timescales, is not a perfectly static rock. It moves, shifts, cracks, and occasionally flickers with its own brief lights. Future missions, especially those placing long-lived stations or telescopes on or near known TLP hotspots, may finally catch these events in multiple wavelengths and tie them definitively to physical processes. Until then, the moon's sporadic glows remain another reminder that even familiar worlds have behaviors we don't fully understand. The moon affects animal behavior, even humans. For as long as humans have watched the sky, we've suspected that the moon's cycles do more than move tides. Folklore across cultures links full moons to madness, crime, fertility, and strange behavior. The very word lunatic comes from luna, the Latin word for moon. For centuries, these beliefs sat mostly in the realm of myth and superstition. But as biologists and psychologists have looked more closely, they've found that while the moon doesn't cast spells, it does exert a subtler influence on life, including us. Start with the clearest case, tides. The moon's gravity doesn't just raise and lower sea levels. It shapes entire coastal ecosystems. Many marine species have evolved life cycles tuned to the lunar rhythm. Their behavior isn't metaphorically lunar, it's literally driven by the moon's cycle. Take the grunion, a small fish along the Pacific coast of North America. These fish come ashore to spawn in synchrony with the full and new moons. During the highest spring tides, massive numbers of grunion ride waves onto sandy beaches, wriggle up the shore, and lay eggs in the wet sand. 2 weeks later, when the tides again rise to their peaks, The waves excavate the buried eggs, and the newly hatched fish are swept back to the sea. The entire reproductive process is tuned to the gravitational cycle set by the moon. Coral reefs offer another striking example. On the Great Barrier Reef and elsewhere, many coral species engage in mass spawning events timed to specific lunar phases. Once a year, often a few days after a full moon, countless coral colonies release clouds of eggs and sperm into the water simultaneously, creating spectacular, swirling blizzards of life. The timing is so precise that scientists can predict these events to the night, even the hour. The moon acts as a clock that helps coordinate reproduction across miles of reef. On land, nocturnal creatures adjust their activity based on how much moonlight is available. Predators and prey both respond. Studies have found that lions in parts of Africa hunt more successfully during darker moon phases, when their prey is less able to see them. Some rodent species reduce their foraging during bright, moonlit nights to avoid being spotted by owls and other predators. Owls themselves adjust hunting behavior with lunar illumination. Insects, too, change feeding and mating habits based on the moon's brightness. Migratory birds sometimes use the moon and stars for navigation, orienting themselves against the sky. Some species of insects and amphibians rely on lunar cues for breeding or calling patterns. The moon, in all these cases, serves as part of the environmental information field organisms use, along with temperature, day length, and seasonal changes. Humans, living under artificial lights in urban environments, might seem insulated from all this, yet the moon's cultural and psychological footprint on us is enormous. The belief that full moons disrupt human behavior persists in hospitals, police departments, and popular belief. Many nurses, doctors, and emergency responders claim that full moons correspond to spikes in admissions, accidents, or erratic behavior. Large-scale statistical studies have tried to test these claims. When researchers look at hospital admissions, crime reports, or birth rates over long periods and compare them to lunar phases, the results are generally mixed or show only very small effects. Most robust analyses do not find dramatic, repeatable surges in crime or psychiatric emergencies tied strictly to full moons. Confirmation, bias remembering nights when weird events and a full moon coincided. Forgetting the many full moons when nothing unusual happened plays a big role. However, some findings hint at more subtle influences, particularly on sleep. A 2013 study published in the journal Current Biology examined sleep lab data collected under controlled conditions. Participants were unaware of the lunar phase and had no view of the sky. Yet during the days surrounding the full moon, they took longer to fall asleep, slept less overall, and spent less time in deep sleep. Their melatonin levels, a hormone tied to circadian rhythms, were also slightly reduced. The effect wasn't huge, but it was measurable. It suggested that human physiology may retain some sensitivity, direct or indirect, to the lunar cycle. Other research has found small correlations between lunar phase and the timing of seizures in some epilepsy patients, or fluctuations in mood or anxiety in certain groups. None of these are universal or strong enough to support folklore about full moon madness, but they suggest that for vulnerable individuals, even small shifts in light exposure or sleep patterns can matter. One straightforward mechanism is moonlight itself. Before widespread artificial lighting, a full moon turned night into a much brighter environment. That extra light could easily disrupt sleep, encourage more nighttime activity, and affect hormone cycles. Over many generations, those rhythms might have left faint imprints in human behavior. Even today, people who camp outdoors or live in low-light regions sometimes report more restless nights around full moons. Beyond humans, controlled studies of animals in captivity and in the wild have repeatedly shown behavioral changes correlated with the lunar phase's altered activity levels, mating efforts, migration timings, and feeding patterns. These aren't magical effects. They're logical adaptations to a predictable 29.5-day cycle of light and gravitational influence. So no, the moon doesn't transform people into werewolves or drive entire cities insane once a month, but it does whisper into the background of biology. It pulls on our oceans, shapes coastlines, sets the timing for corals and fish, nudges predators and prey, and tugs at our sleep and hormones in small ways. Its influence is not one of brute force, but of rhythm. For billions of years, Life on Earth has grown up under a sky that brightens and darkens with a reliable lunar beat. Even if we've drowned that signal in neon and LED glare, the echo of that ancient clock may still tick softly in our biology. The moon has water, but it's trapped in strange ways. For much of the 20th century, the moon was considered bone dry. Early analyses of Apollo rocks found no obvious water. The surface is exposed to vacuum and intense solar radiation. There are no clouds, lakes, or streams. The default assumption was that the moon was a desiccated desert from top to bottom. That picture has been overturned. Not only is there water on the moon, it's present in more forms and places than anyone imagined, and the details are odd. The first major surprise came not from new missions, but from new laboratory techniques. Apollo rocks that were once thought to be completely dry were re-examined with more sensitive instruments decades after they were collected. Inside tiny volcanic glass beads formed in explosive fire fountain eruptions, scientists found small but real amounts of water locked away. This implied that the moon's interior magma once contained water, challenging the idea that it was entirely dehydrated during formation. Then came direct evidence of surface and near-surface water. In 2009, NASA's L-Cross mission deliberately crashed a spent rocket stage into a permanently shadowed crater near the lunar South Pole. Instruments on a following spacecraft analyzed the plume of material thrown up by the impact. Within that plume, they detected clear spectral signatures of water ice, along with other volatiles. Permanently shadowed regions, deep craters near the poles that never see sunlight because of the moon's small axial tilt act as cold traps. Temperatures inside can drop below 200 degrees C, cold enough to freeze and preserve water and other volatiles for billions of years. Comets, icy asteroids, and even the slow accumulation of hydrogen and oxygen from the solar wind may have delivered water molecules there, where they became trapped as ice in the dark regolith. Estimates vary, but there could be hundreds of millions to billions of tons of water ice locked in these polar cold traps. That's already transformative. Water is heavy and expensive to launch from Earth. Ice on the moon can be melted for drinking, split into oxygen for breathing, and into hydrogen and oxygen for rocket propellant. Access to local water is one of the main reasons the lunar South Pole is a prime target for future missions and potential bases. But that's not the only kind of lunar water. In 2018, using data from the Moon Mineralogy Mapper instrument, scientists confirmed that small amounts of water and hydroxyl, OH, are present across much of the lunar surface, even on sunlit regions. This isn't water in puddles or ice patches. It's molecules chemically bound to minerals in the regolith, or possibly trapped in tiny glassy beads created by micrometeoroid impacts. This surface-bound water behaves strangely. It seems to migrate over the course of a lunar day. As temperatures rise, some molecules may detach from grains and hop along the surface, moving toward colder or shadier areas. As the surface cools again, they can reattach or freeze. This kind of ultra-thin, stop-and-go water cycle is nothing like Earth's robust hydrological engine, but it's a kind of water cycle nonetheless, operating molecule by molecule. Where does this widely distributed water come from? Several sources are likely at work: comets and asteroids. Impacts by water. Rich bodies throughout lunar history would deliver both ice and trapped water to the surface and subsurface. Solar wind. Hydrogen ions from the sun constantly bombard the lunar surface. When these protons encounter oxygen in the regolith, they can form hydroxyl and water molecules that become loosely attached to mineral grains. Volcanic outgassing. Ancient lunar volcanism may have brought water from the interior to the surface, some of which remain bound in glasses and minerals. The fact that we now see evidence for interior water, polar ice, and surface-bound molecules paints a much more complex picture of the moon's history. It was once assumed that the giant impact that formed the moon would have boiled off nearly all volatiles. The presence of water suggests either that not all of it was lost, or that water was reacquired later in significant quantities, or both. For future explorers, the distribution and accessibility of lunar water is a central concern. Ice in permanently shadowed craters will be hard to reach. These regions are extremely cold and never receive direct sunlight. Mining them would require specialized equipment and power systems. Water-bound in regolith across the surface is even more diffuse. Extracting it would mean heating large volumes of soil to release modest amounts of vapor, technically possible, but energy intensive. Still, knowing it's there changes everything. The moon is not a completely dry rock. It hosts reservoirs of one of the most valuable substances in space, stored in forms that are challenging, but not impossible to tap. Scientifically, lunar water holds clues about how water was distributed throughout the inner solar system, how surfaces interact with the solar wind, and how planetary bodies acquire and hang onto volatiles. So the next time you look up at the seemingly barren, dust-covered moon, remember that under that hostile surface, in polar shadows and within grains of rock, water is hiding. Not flowing in rivers or filling oceans, but locked, scattered, and cycling in ways we're only beginning to map. The moon's gravity is uneven and mysterious. From far away, the moon looks like a smooth, regular sphere quietly circling Earth. You'd expect its gravity to be similarly smooth, a simple, predictable pull, decreasing with distance. But when spacecraft began orbiting the moon closely, that expectation fell apart. The lunar gravitational field turned out to be oddly lumpy. In some regions, gravity is noticeably stronger than it should be. In others, it's slightly weaker. These anomalies are so pronounced they've disrupted and even crashed spacecraft. The culprits are what scientists call mass concentrations, or mascons regions in the lunar crust and upper mantle where extra mass is buried beneath the surface. These hidden structures tug more strongly on anything passing overhead. For a low-orbiting spacecraft, flying over a mascon is like rolling over a gravitational pothole in reverse, a brief extra pull that alters its trajectory. The existence of mascons was first inferred in the 1960s, when NASA's lunar orbiter spacecraft, precursors to Apollo, started behaving unpredictably. Their orbits, calculated in advance with high precision, kept drifting in ways engineers couldn't account for. The deviations were small, but consistent. It soon became clear that something in the moon itself was pulling on them, something asymmetric. Careful tracking revealed that these gravitational hotspots were concentrated beneath the largest dark maria, the vast circular plains visible from Earth, such as Mare Imbrium, Mare Serenitatis, Mare Crisium, and others. These maria mark ancient impact basins, huge craters formed when colossal asteroids or planetesimals slammed into the moon billions of years ago. After those impacts, molten material welled up from the interior and flooded the basins with basaltic lava. Initially, scientists thought the extra mass might simply be the dense basalt filling these basins. But the numbers didn't add up. The lava alone wasn't heavy enough to explain the strength of the mascons. Something deeper and denser seemed to be lurking below. Several explanations have been proposed. One is that the impacts that form the basins compress the lunar mantle beneath them, creating denser zones that now act as gravitational anchors. Another is that fragments of the impactors themselves, possibly metallic cores of differentiated bodies, remained embedded deep under the basins. It's also possible that upwellings of denser mantle material rose toward the crust after the impacts and then solidified. To untangle this, NASA launched the GRAIL mission in 2011. GRAIL consisted of two small spacecraft, Ebb and Flow, that flew in tight formation around the moon. By measuring tiny changes in the distance between them as they passed over regions of stronger and weaker gravity, scientists were able to map the moon's gravitational field in extraordinary detail. The resulting gravity maps are like an X-ray of the moon's interior structure. They confirm that mascons under major basins are compact, highly dense regions embedded in the crust and upper mantle. The maps also revealed a patchwork of other anomalies, fossil remnants of ancient lava tubes, buried craters, and internal fractures that tell a story of a moon that was once much more active and dynamic. From a practical standpoint, these gravity variations matter a great deal. Any spacecraft in low lunar orbit has to contend with an uneven gravitational pull. If mission planners ignore mascons, a probe's orbit can slowly change shape and altitude until it either escapes or smashes into the surface. Early Soviet missions like Luna 15, which crashed in 1969 while Apollo 11 was on the surface, suffered in part from incomplete knowledge of the lunar gravity field. Thanks to Grail and follow-up work, modern missions have highly accurate gravity models. Engineers now build these into navigation and landing calculations, adjusting trajectories and fuel budgets accordingly. Future lunar satellites, communications relays, and orbiting stations will all rely on this knowledge to stay where they're supposed to be. There's also a deeper comparison to be made. Earth, despite having mountains, trenches, and a turbulent interior, has a relatively smooth gravity field at large scales. Its active geology, fluid outer core, and mobile mantle help average out mass differences over time. The Moon, smaller and long solidified, has no such internal mixing. Its crust preserves sharp contrasts and density frozen scars of massive impacts, volcanic episodes, and internal rearrangements. In other words, the Moon's wild gravity is partly a consequence of its age and inactivity. It's a fossil record of its own violent past, written not just in craters and basins, but in invisible mass distributions beneath. Those lumpy pulls and hidden weights are messages from a deep interior we can't see directly. The same side always faces us, and that's not a coincidence. One of the strangest and most easily overlooked facts about the Moon is also the most obvious. We always see the same face. Night after night, from anywhere on Earth, the pattern of lunar dark and light regions is the same. The man in the moon, the rabbit, whatever shape you perceive it, never rotates away. Yet the Moon is rotating. It spins, once every orbit. This condition is called tidal locking, and it's not a visual trick. It's the end result of a long gravitational struggle played out over millions of years. When the Moon first formed, it probably spun much faster, showing different faces to Earth over time. But Earth's gravity pulled on any slight asymmetry in the Moon's mass distribution bulges, irregularities, or elongations. Those pulls acted like a brake on the Moon's rotation. Over time, friction inside the Moon converted rotational energy into heat, slowing its spin. Eventually, the Moon's rotation period matched its orbital period. At that point, one hemisphere always faced Earth, and the torques that had been slowing it essentially vanished. The system reached a stable configuration. Tidal locking isn't unique to our Moon. Many of the larger moons in the solar system are tidally locked to their parent planets. Some exoplanets orbiting very close to their stars are probably locked as well, with permanent day and permanent night sides. Whenever two bodies interact gravitationally over long enough timescales, with enough internal friction, locking is a likely outcome. What makes our case special is that we're on the side doing the observing. We're on the planet seeing only one face of our companion. For most of human history, the far side of the Moon was literally unknowable. It never rotated into view. Stories and speculation filled the gap. Was it the same? Different? Home to something hidden? We got our first answer in 1959 when Luna 3 flew around the back and sent back fuzzy photos. The far side was real, alien-looking, and heavily cratered. Since then, many spacecraft have mapped it, and one mission has landed there. Yet even now, most people's mental image of the Moon is of the near side only. The locked view still shapes our psychological relationship with it. The locking isn't perfectly rigid. Because the Moon's orbit is slightly elliptical and its axis is slightly tilted, we see a small apparent wobble called libration. Over the course of a month, libration lets us peek a little bit around the edges, revealing up to about 59% of the lunar surface from Earth over time, rather than an exact 50%. But the basic fact remains. The same central face is always turned toward us. This tidal relationship runs both ways. The Moon's pull on Earth is slowing our rotation, as we've seen, and gradually pushing the Moon outward. Over unimaginably long periods, Earth could also become tidally locked to the Moon, so that one side of Earth would always face it. Whether the solar system survives long enough for that to happen is another question. Tidal locking does more than create a familiar face. It has shaped myth, navigation, and science, Because the same features are always in view, ancient peoples could use them as reliable sky markers. Apollo mission planners could choose and rehearse landing sites based on telescopic maps. Poets could write about the face of the moon, knowing it would mean the same thing across cultures. It also hints at underlying gravitational asymmetries. The fact that the moon's center of mass is offset slightly toward Earth, and that its near side has different structure and density than the far side, likely helped lock it in this particular orientation. It's not just locked, it's locked in a specific way that keeps that particular hemisphere turned toward us. So when you look up and see the same pattern of seas and highlands you've seen since childhood, remember that it's not an accident. It's the visible outcome of billions of years of tidal friction, mass distribution, and orbital evolution. A cosmic compromise between two bodies that have been tugging on each other since they formed. The moon stabilizes, Earth's tilt, and without it, life might not exist. Earth's axis is tilted about 23.5 degrees relative to its orbit around the sun. That tilt is why we have seasons. As we go around the sun, different hemispheres lean toward or away from it, changing how sunlight is distributed across the planet. Without axial tilt, there would still be climate differences by latitude, hotter at the equator, colder at the poles, but no true seasons. But that tilt is not fixed in stone. Left alone, a planet's axis can wobble dramatically over long timescales, especially if it's influenced by gravitational tugs from other planets. Computer simulations of Earth without its moon suggest that our tilt might vary chaotically between near zero and over 60 degrees. At high tilts, the poles could point almost directly at the sun part of the year, baking under continuous daylight, while equatorial regions freeze. Then over tens or hundreds of thousands of years, the configuration could shift again, plunging previously warm zones into cold and vice versa. Such wild swings would wreak havoc on climate stability. Ice caps would advance and retreat unpredictably. Deserts, forests, and oceans would be shoved in and out of habitable ranges. It would be far harder for complex ecosystems to adapt, and for long-lived climate-sensitive species, like us, to evolve and persist. The moon changes this story. Its substantial mass, unusually large for a planetary satellite, acts as a stabilizing influence on Earth's spin axis. The Earth-Moon system behaves like a gyroscope, with the moon's gravitational pull reducing the amplitude of Earth's axial wobble. Instead of chaotic flips, Earth's tilt oscillates only slightly, between about 22 and 24.5 degrees, over a cycle of roughly 41,000 years. Those small variations contribute to Ice Age cycles, but don't completely destabilize the planet. This stabilizing role may have been crucial for life as we know it. A reasonably steady tilt gives Earth long-term climate zones, tropics, temperate regions, polar areas that remain broadly consistent over millions of years. That environmental predictability allows complex life to diversify, ecosystems to mature, and evolutionary experiments to play out without being reset too frequently by planetary-scale catastrophes. The Moon is unusually large relative to Earth. Its diameter is about 1/4 of Earth's, and its mass is about 1/81 of Earth's. No other rocky planet in the solar system has a moon this big compared to itself. Mars's small moons are more like captured asteroids. Venus and Mercury have none. The Earth-Moon pair is, in some ways, more like a binary planet system than a typical planet-moon setup. If the giant impact hypothesis is correct, this odd configuration may be a direct consequence of that ancient collision with Theia. The impact could have spun Earth up, altered its tilt, and provided the mass that later became the Moon, setting up a combined system uniquely suited to long-term stability. Without the Moon, Earth's history would likely look very different. It might still host life, but the path from simple microbes to complex, climate-sensitive organisms and civilizations could be much more precarious. Some climate models suggest that without lunar stabilization, Earth might experience extreme icehouse and greenhouse states driven by chaotic tilt changes, potentially sterilizing land surfaces at intervals. We can't run that alternate history, but we can see hints of what tilt chaos looks like by studying Mars. Mars has no large moon to stabilize it. Its axial tilt varies widely, from about 10 to 60 degrees over millions of years. Evidence in Martian polar deposits suggests that its climate and ice distribution have changed dramatically in step with these shifts. In that light, the moon is more than a nighttime ornament. It is part of the invisible architecture that has kept Earth clement for billions of years. It doesn't create life, but it shapes the stage on which life unfolds, limiting the wildest swings, damping the most extreme possibilities, and giving evolution a stable enough platform to work with. The moon was once much closer, and the Earth had 5-hour days. Today, the moon feels comfortably distant, hanging some 300 and maybe 400 kilometers away on average. It rises and sets slowly. Its face changes gradually over weeks. Our 24-hour day feels natural, but rewind deep into Earth's past, and the configuration was radically different. The moon once loomed far larger in the sky, and Earth spun so fast that a full day lasted only a few hours. Right after the moon formed, likely from the giant impact that shattered and reassembled the proto-Earth and Theia, it orbited much closer, perhaps only 20,000 to 30,000 kilometers above Earth's surface. That's roughly 14 times closer than it is now. At that distance, the moon would have appeared perhaps 15 to 20 times wider in the sky than today, dominating the heavens like a huge glowing disk. Meanwhile, Earth's rotation would have been much faster. Some models suggest that early Earth may have spun once every 4 to 6 hours. The sun would race across the sky. Tides, driven by that oversized nearby moon, would have been colossal, not just in the oceans, but felt in the partially molten crust as well. Those tides would have poured enormous energy into Earth's interior and oceans, generating intense heating, strong currents, and frequent coastal flooding and draining. The Earth-Moon system in those early days was a tempestuous partnership, with tides, rotation, and orbits all exchanging energy at a furious rate. Over time, tidal friction drag caused by the misaligned tidal bulges slowed Earth's spin and transferred angular momentum to the moon's orbit. The moon spiraled outward. Earth's day stretched. Geological and fossil records give us checkpoints along this evolution. Around 620 million years ago, evidence from tidal deposits suggests that a day lasted around 21.9 hours. Around 1.4 billion years ago, it was about 18 hours. Go back far enough, and you reach those 5-hour days. The fact that Earth's rotation is slowing and the moon is retreating is not just abstract dynamics. It may have influenced the conditions for life. Stronger, more extreme tides on the early Earth could have helped mix the oceans, concentrating chemicals and nutrients in intertidal zones. Some hypotheses about the origin of life emphasize the role of wet-dry cycles and tidal pools in driving prebiotic chemistry. A closer moon would have made those cycles more dramatic. As days lengthened, the pacing of environmental cycles changed. Longer daylight periods and nights altered how heat was distributed and how early organisms experienced their world. Over immense spans of time, life adapted to and co-evolved with this slowly changing clock. We live now in a relatively middle-aged configuration. The moon is no longer a looming giant, but not yet so distant that it only produces weak eclipses. Our day is 24 hours, not 4 or 40. Tides are strong enough to sculpt coasts and ecosystems, but not so extreme as to be globally catastrophic. It's one more reminder that what feels permanent is actually temporary. The Earth-Moon system has been evolving since its birth and will continue to change long after we're gone. There may have been a second moon. We're used to thinking of the moon as a singular companion, the moon, not a moon. It feels permanent and solitary, the one constant presence orbiting Earth. But some planetary scientists have suggested that this hasn't always been the case. According to one hypothesis, Earth may once have had not one moon, but two. And the second one didn't simply drift away. It may have merged with the one we see now, leaving behind clues written into the lunar surface. This idea arises from one of the moon's strangest features, the stark difference between its near side and far side. The near side, which always faces Earth, is relatively low and smooth in many regions, covered by dark basaltic plains known as Maria. The far side, by contrast, is thickly cratered, mountainous, and almost entirely lacking those large dark seas. The crust on the far side is significantly thicker on average than on the near side. This asymmetry has puzzled scientists for decades. In 2011, planetary scientists Martin Utzi and Eric Asfow proposed a bold explanation. Perhaps the moon's far side is the scar of a long-ago merger with a smaller companion moon. In their model, the same giant impact that created the moon also produced multiple moonlet small satellites orbiting Earth along with the main one. Over time, orbital interactions caused one of these smaller moons, perhaps around 1,000 kilometers in diameter, to slowly drift toward the larger moon. Because their relative velocities would have been low compared to typical impact speeds in the solar system, the collision would not have been a violent, catastrophic smash-up. Instead, the little moon might have gently crashed into the bigger one at a few kilometers per second, enough to deform and redistribute crust, but not enough to vaporize everything. The smaller body would effectively splat onto one hemisphere of the larger moon, piling its material onto the surface and thickening the crust there. Computer simulations suggest that such a low-velocity merger could create a lopsided moon with a thicker, more mountainous far-side crust, and a thinner, more volcanic near side, very much like what we observe. It could also help explain subtle differences in composition and internal layering between the two hemispheres. In this scenario, the second moon is gone in any distinct sense. Its core and mantle would have been smeared, mixed, and absorbed into the surviving moon. What remains of it is the far side highlands, a rugged shell of redistributed crust, the leftovers of a long-lost sibling. The hypothesis is attractive because it ties together several observations with a single event: crustal thickness variation, the paucity of Maria on the far side, and the distinct topography. But it's also hard to confirm. We don't have direct samples from the far side highlands to analyze for unique chemical signatures. Most of the moon rocks we've studied come from the near side. Lunar meteorites, which come from random locations, do offer glimpses, but their origins are hard to pin down precisely. Other models exist that don't require a second moon. Some suggest that differences in heat flow and mantle composition between the near and far sides led to asymmetric volcanic activity. Others invoke the influence of Earth's early radiation and tides on how the moon's crust crystallized. So far, no single explanation has universally won out. Still, the two moons hypothesis highlights just how chaotic and temporary planetary systems can be. Early on, Earth could have had multiple sizable satellites, some of which merged, fell back to Earth, or were ejected. Even today, Earth occasionally captures small asteroids into temporary orbits, mini-moons, that stay for a while before leaving again. If the smaller ancient moon did exist, then in a sense, it hasn't vanished completely. It's still there, fused into the bulk of the far side crust, its individuality erased, but its mass preserved. The moon we see now would then be a composite object, the final product of a quiet cosmic cannibalism. Ancient cultures describe the time before the moon. To us, the moon feels timeless. Every known human culture has stories, myths, and calendars that include it. It's so deeply woven into our experience that we naturally assume it's always been in the sky, exactly as it is now. But scattered across ancient traditions are stories that speak of a time when there was no moon, a pre-lunar era when the night sky was different. The ancient Greeks had a word for people who supposedly lived in such a time: proselenes, literally, before the moon. Some older texts describe the Arcadians, a people of central Greece, as proselenes. Later writers, including Aristotle, mention tales of humans, or proto-humans, who existed before the moon appeared in the heavens. These weren't meant as scientific accounts, but they treated the moon's arrival as a distinct event. In Colombia, the Muisca Chibcha, people told of a time when the world was in disorder and the moon did not yet shine. In their mythology, a female figure often associated with water, fertility, or chaos became the moon, rising into the sky and bringing order to time and agricultural cycles. Zulu oral traditions from southern Africa include stories in which the moon was created or placed in the sky by two brothers or deities. Prior to that act, they say, nights were pitch black. The implication is that the moon was not always there. it had a beginning. In some Inuit lore, the moon is sometimes portrayed as a transformed human or an entity that ascended to the sky. Certain versions frame this as a relatively recent event in mythic time, not as something primordial. What are we to make of these stories? Most historians and anthropologists view them as symbolic narratives rather than literal records. Myths often encode big transitions, shifts in climate, the advent of agriculture, major celestial events like comets or eclipses, in metaphorical terms. Before the moon might reflect a time before standardized lunar calendars, or before certain rituals were codified. It might describe an age of perceived chaos before societal order was established. From a scientific standpoint, the moon formed very early in Earth's history, around 5 billion years ago, long before life emerged, let alone humans. There is no accepted evidence that the moon arrived late enough for human or even pre-human eyes to witness the change. Planetary dynamics and radiometric dating both point to an ancient moon. Some fringe theories speculate that the moon may have been captured into its present orbit more recently than mainstream models allow, and that early humans may have seen the sky without it. These ideas typically conflict with well-established geological and orbital evidence. They remain outside scientific consensus. Another possibility is that these before the moon traditions preserve an intuitive recognition that the moon is not eternal. Ancient observers might not have known when or how it formed, but they intuited that it had a beginning, just as they told stories about the creation of the sun, stars, and Earth. They told stories about the appearance of the moon. Regardless of their origin, such myths highlight how strongly humans sense that the sky, like Earth, has a history. Even without telescopes or physics, early cultures grasped that the world above is not static. In a poetic way, tales of a time before the moon echo a genuine scientific truth. The moon did not exist forever. It entered the story of Earth at some point, and when it did, it changed everything, from tides and climate to the rhythms by which early humans counted days and seasons. The moon has a very thin atmosphere, called an exosphere. The phrase airless moon is mostly accurate, but not completely. The moon doesn't have an atmosphere in any familiar sense. There's no breathable air, no clouds, no weather. But it does have a wisp of gases clinging to it, a barely there envelope called an exosphere. In a conventional atmosphere like Earth's, gas molecules collide with each other constantly, behaving like a fluid. Pressure, winds, convection, and weather patterns emerge from those interactions. An exosphere is different. It's the outermost, most rarefied part of an atmosphere, where particles are so sparse they almost never collide. On small bodies like the moon, the entire atmosphere is essentially just an exosphere. The lunar exosphere is vanishingly thin. Near the surface, there are only on the order of tens to hundreds of molecules per cubic centimeter, compared to about 10 billion molecules per cubic centimeter in Earth's lower atmosphere. If you could stand on the moon without a suit and survive the vacuum in other ways, you would not feel any air. The pressure is effectively zero. Yet this ghost atmosphere exists and can be measured. It's composed of several components: helium, neon, argon, hydrogen, sodium, potassium, and trace amounts of other species, including bits of water vapor and oxygen-bearing molecules. Where do these gases come from? Several processes contribute. Outgassing. Radioactive decay in the lunar interior produces gases like argon and helium that slowly seep upward and escape at weak points in the crust. Solar wind sputtering. Charged particles from the sun bombard the surface, knocking individual atoms off the regolith into ballistic trajectories. Micrometeoroid impacts. Tiny impacts vaporize bits of rock and soil, creating transient local clouds of gas and dust. Earth's extended atmosphere. Oxygen ions from Earth's upper atmosphere can reach the moon when it passes through our magnetotail, adding a faint trickle of oxygen to the mix. Once in the exosphere, these particles follow long, arcing paths above the surface. Because collisions are so rare, each atom or molecule essentially travels independently, rising and falling like a thrown ball under the influence of lunar gravity until it either re-impacts the surface, gets knocked away, or escapes into space. The exosphere is dynamic. Its composition and density vary with time of day, solar activity, and even meteor showers. For example, sodium and potassium become more abundant and form extended clouds or tails when the moon is hit by more micrometeoroids. Helium density can change with solar wind conditions. Radon has been detected in localized bursts, indicating specific outgassing events. Studying this fragile envelope isn't just an academic exercise. It provides clues about the moon's interior, its interaction with the solar environment, and the processes that shape airless bodies throughout the solar system. Mercury, some asteroids, and even icy moons like Europa and Ganymede also have exospheres, governed by similar physics. Understanding the moon's exosphere helps us understand them as well. There's also a practical angle. As human activity on the moon increases, landers, rovers, habitats, mining operations, our exhaust plumes and disturbances will inject new gases and dust into the exosphere. Because it's so delicate, even small additions can alter its composition. Future missions are already planning instruments to monitor these changes, both to learn more science and to avoid contaminating measurements of the moon's natural state. So while it's fair to say, the moon has no atmosphere like ours, it isn't wrapped in perfect nothingness. It sits inside a faint, shifting haze of atoms. An exosphere so tenuous it took us landing instruments there to truly confirm it, and so delicate that a single rocket landing can briefly change its character. Moon dust is so sharp, it can damage lungs and equipment. Dust on Earth is usually more nuisance than threat. It's soft, rounded, and often made from organic material or weathered minerals. Lunar dust is another story. On the moon, the fine gray powder covering everything, the regolith is one of the biggest hazards for both machines and people. The difference comes down to environment. On Earth, rocks are broken down by weathering, wind, water, chemical reactions, and biological activity. Over time, these processes smooth and round particles. On the moon, there is no wind, no flowing water, no biology. The main process grinding rocks into dust is impact. For billions of years, micrometeoroids and larger meteoroids have slammed into the lunar surface at high speeds. Each impact fractures rocks, melts some material, and blasts sharp fragments in all directions. Repeated impacts grind those fragments finer and finer, but never smooth them. Under a microscope, lunar dust grains look like shards of broken glass, jagged, angular, and abrasive. The Apollo astronauts discovered this firsthand. As soon as they stepped onto the surface, the dust clung to their boots, suits, and equipment. It infiltrated joints and seals. Despite efforts to brush off before returning to the lunar module, it got inside. Once in the cabin, it floated in microgravity, stuck to everything, and was impossible to fully contain. The dust proved highly abrasive. It scratched visors, wore down outer suit layers, and caused hinges and zippers to grind. Tools and equipment showed unexpected wear after just a few days of exposure. Astronauts reported that the dust smelled faintly like spent gunpowder when brought into contact with a sign of its chemically reactive, freshly fractured surfaces. Beyond equipment, there are serious concerns about health. Inhaling fine, sharp mineral dust can damage lungs. On Earth, prolonged exposure to dust containing silica or other minerals can cause diseases like silicosis and increase the risk of lung cancer. Lunar dust appears to be at least as dangerous, if not more, because its particles are more angular and unweathered, and possibly rich in reactive surface bonds. During Apollo 17, astronaut Harrison Schmitt experienced lunar hay fever, sneezing, watery eyes, and throat irritation after breathing air that had been contaminated with dust. His symptoms subsided, but they were a warning. In future long-duration lunar missions, astronauts could be exposed to much more dust over much longer periods. Lunar dust also carries electrostatic charge. Under solar UV radiation, dust grains can accumulate charge and even levitate a bit above the surface, especially at the day-night boundary. This behavior may contribute to a strange horizon glow observed by some Apollo astronauts and earlier spacecraft faint lights scattering from charged dust hovering above the ground. For hardware designers, dust is a nightmare. It can obscure solar panels, foul radiators, clog mechanical systems, and degrade seals. For habitat designers, it's both an engineering and biomedical problem. Future lunar bases will need robust dust mitigation strategies. Airlocks that trap and filter dust, suit port systems where suits stay outside while astronauts enter and exit through rear hatches, self-cleaning materials, and perhaps electrostatic brooms or fields to repel particles. Researchers on Earth use lunar, regolith, simulants artificial blends of crushed basalt and other minerals with similar grain sizes and compositions to test how dust affects equipment and biology. These experiments consistently underscore the same point. If we plan to live and work on the moon, we have to treat the regolith not just as soil, but as a pervasive, sharp, chemically active hazard. The moon's dust is part of what gives it its beauty. Those fine gray layers that record eons of impacts, the soft-looking surface that took our first off-world footprints. But beneath that softness is a field of microscopic blades, waiting to cling to every surface and infiltrate every crack. There are unexplained lights on the lunar surface. For such a stark, seemingly motionless world, the moon has a long record of doing something baffling, occasionally lighting up in ways no one fully understands. These aren't reflections from spacecraft or stars. They're brief, localized brightenings on or just above the surface, called transient lunar phenomena, TLPs. Reports go back centuries. Medieval monks, early telescopic observers, 18th and 19th century astronomers, many claim to see short-lived flashes, glows, or color changes on the moon. Over time, hundreds of such events were cataloged. Some appeared as pinpoint flashes, others as fuzzy patches that brightened and faded. Certain hotspots, like Aristarchus Crater, appear in these reports again and again. With modern instruments, we now know that at least some TLPs are real physical events. High-sensitivity telescopes have directly recorded small meteoroids slamming into the moon and producing bright millisecond-to-second flashes. Those impacts do happen frequently, but the complete catalog of TLPs is more varied and puzzling than just impacts. Gas release is one suspect. The moon still has trace internal gases, and when they escape, they might briefly interact with sunlight or charged particles to create faint glows. Electrostatic dust lofting and discharges at the day-night boundary may also create momentary luminous phenomena. Moonquakes disturbing the surface could stir dust and trigger electric effects. Yet, not every reported TLP has been matched to one of these mechanisms. The combination of rarity, unpredictability, and faintness makes systematic study hard. Robotic telescopes now monitor the moon for these events, and as more are captured with multiple instruments, we may finally sort illusion from genuine lunar activity. For now, some small part of the moon's behavior literally remains a flicker in the dark. Some scientists think the moon may be hollow. Few lunar ideas capture the imagination like the notion of a hollow moon. It sounds like pure science fiction, a vast shell with empty space inside, perhaps even an artificial construct. In fringe circles, this hypothesis has been used to explain everything from strange seismic data to odd orbital behavior. But it has a kernel in real science. Early seismic experiments did reveal unexpected properties of the lunar interior. When Apollo astronauts set up seismometers and then deliberately crashed spent rocket stages or lunar modules into the moon, the resulting vibrations lasted far longer than comparable quakes on Earth. The moon rang for hours. Some interpreted this as evidence that the moon is hollow or extensively cavernous. In reality, it tells us more about material properties than emptiness. The moon is extremely dry and rigid compared to Earth. Without liquid water and large molten regions to absorb and scatter seismic waves, mechanical energy travels farther and decays more slowly. The crust and mantle behave more like a solid crystal than a dampened, semi-molten mix. That alone can produce the bell-like ringing effect. Modern gravity mapping, like NASA's Grail mission, and refined seismic models indicate that the moon has a layered interior, a crust, a mantle, and a small core, with both solid and liquid components. Its density profile is inconsistent with a mostly hollow structure. We find no signs of giant empty voids on planetary scale. Still, the hollow moon idea persists culturally because it taps into something deeper. The feeling that the moon is too strange, too neatly placed, too important to be just another rock. In that sense, it's less a theory and more an expression of unease with coincidence and incompleteness in our models. Scientifically, the moon is not hollow, but the anomalies that spawned the idea, the long-lasting quakes, the odd orbit, the unique size are real puzzles that continue to demand explanation. China's moon missions found something weird in the soil. For decades after Apollo and the Soviet lunar missions, the moon went unvisited by sample return missions. Then, in 2020, China's Chang'e 5 probe landed, scooped, drilled, and lifted off again, delivering fresh lunar material to Earth for the first time in over 40 years. It chose a younger volcanic region, Oceanus Procellarum, rather than the older highlands, or Maria visited by Apollo. The goal was to fill a gap in our understanding of more recent lunar volcanism. Among the returned samples, Chinese scientists identified a completely new mineral, Chang'e, Y, a phosphate mineral found in tiny crystals within the lunar basalt. While chemically related to known phosphate structures on Earth, this exact mineral had never been seen before. Its presence tells us about how rare Earth and phosphate elements crystallized in young lunar magmas. The samples also contain measurable amounts of helium-3, a rare isotope barely present on Earth, but more abundant in lunar soil thanks to billions of years of solar wind implantation. Helium-3 has been proposed as a potential fuel for advanced nuclear fusion reactors. We're far from harnessing that in practice, but the confirmation of helium-3 in new lunar samples keeps alive the idea of the moon as a future fusion fuel resource. Earlier, China's Chang'e 4 rover on the far side reported a strange, glassy, dark gel-like material in a small crater, likely impact melt or unusual glass formed in a high-energy collision. It wasn't alive or literally gel, but it was texturally and visually different from surrounding regolith. Combined with mineralogical surprises from Chang'e 5, these findings underscore that the lunar surface is more diverse, chemically and geologically, than the limited Apollo sample set suggested. Some lunar rocks found on Earth got here naturally. It's not only humans who have carried lunar rocks to Earth. Nature has been doing it for eons. When large meteoroids or asteroids strike the moon, the impact can be energetic enough to blast chunks of rock up and out of lunar gravity. Some of that debris enters heliocentric orbits and, after long journeys, a tiny fraction intersects Earth's path and falls as meteorites. Today, we've identified hundreds of meteorites that originated from the moon. They were discovered in deserts and Antarctic ice fields, where dark rocks stand out and preservation is good. Their lunar origin was confirmed by comparing their mineralogy, chemistry, and trapped gases to Apollo samples. The match is so precise that we can be confident these rocks came from the moon. These natural lunar samples are scientifically valuable because they come from random locations, not just the near-side equatorial zones where Apollo landed. Some contain pieces from deep within the lunar crust or even near the mantle, offering clues to parts of the moon we've never visited. Others are older, or have experienced different impact histories than Apollo rocks. It's a humbling thought. For billions of years, pieces of the moon have been falling to Earth unnoticed. Before we ever went there, fragments of that distant world were already here, lying in fields, deserts, and ice, waiting for us to learn how to recognize them. There are frozen shadows on the moon that haven't seen light for billions of years. Near the lunar poles, sunlight skims the horizon at a low angle. Because the moon's axial tilt is only about 1.5 degrees, some deep craters and depressions in these regions never see direct sunlight at all. Their floors are in permanent shadow, eternally dark, cold traps that have not been illuminated for billions of years. Without sunlight, and with no atmosphere to transport heat, these permanently shadowed regions, PSRs, reach some of the coldest temperatures anywhere in the solar system, as low as 240 degrees or below. At those temperatures, volatile substances like water, carbon dioxide, and even some more exotic ices can remain stable for eons. Remote sensing instruments, including neutron spectrometers, infrared spectrometers, and radar, have detected strong evidence of water ice in many of these PSRs, especially at the South Pole. When L-Cross smashed into one such crater, the resulting plume contained clear signatures of water. The Lunar Reconnaissance Orbiter's thermal maps show frigid, unchanging cold there. These frozen shadows are scientifically priceless. The ices within may capture a record of comet impacts, solar wind deposition, and volatile transport going back to the early solar system. For exploration, there are also resources, stores of water that could sustain astronauts and feed fuel production. But they are also harsh. Any rover or lander venturing into a PSR must function with no direct sunlight, extreme cold, and difficult communication links. NASA's upcoming Viper rover aims to explore some of these regions, drilling into the regolith to map ice content. When we finally roll into those dark craters, we'll be entering places untouched by light since before complex life arose on Earth. Moonlight isn't cold, but many thought it was. For much of history, people believed that moonlight had a chilling, even harmful physical effect. Folk wisdom in various cultures warned against sleeping under direct moonlight, claiming it caused illness, fevers, or moonstroke. Gardeners blamed moonlight for withering plants or spoiling food. Some early experiments even appeared to show that objects left in moonlight became colder than those kept in shade. We now know that moonlight is simply reflected sunlight attenuated and scattered by the lunar surface, but not fundamentally different in nature. Its intensity is far too low to meaningfully cool or heat objects. If anything, standing in moonlight very slightly increases the energy reaching you compared to standing in total darkness. So why did people think otherwise? Partly because nights with a bright full moon are often cooler than day, and people associated the chill with the visible light source. Early scientific experiments that measured the cooling effect of moonlight were usually flawed. They failed to account for radiative heat loss to the cold night sky. An object exposed to the sky will radiate heat away more efficiently than one sheltered, regardless of moonlight. That net loss, not the moon's rays, is what cooled the object. Psychologically, the pale quality of moonlight, its bluish cast, its association with stillness and late hours added to the sense of coldness. Even after the physics became clear, the metaphor of cold moonlight remained potent in language and art. In physical reality, though, moonlight neither chills nor burns. It's a faint echo of the sun, not a mysterious opposite. One moon rock went missing for decades, then turned up in a garage. The rocks brought back by Apollo missions are among the most valuable scientific specimens on Earth. Most are stored and cataloged under strict conditions, but not all lunar rocks have had such careful treatment. Some of the goodwill samples, tiny fragments mounted on plaques and gifted to nations and U.S. states in the 1970s have gone missing, stolen, sold, or simply misplaced. One particularly strange story involves the Apollo 17 Goodwill moon rock presented to Honduras. It vanished from official records and resurfaced decades later in a private sting operation. A former NASA investigator, Joseph Gutheinz, posing as a buyer, traced it to a man in the United States who had obtained it through a retired diplomat. For years, the rock had sat in a box in a garage, an almost priceless piece of another world treated like old memorabilia. Once recovered, it was authenticated and returned. Similar tales have emerged elsewhere. A Goodwill moon rock misfiled in a museum drawer, one suspected lost in a fire, others turning up in estate sales or on the black market. Because these samples are small and embedded in acrylic, they're easy to misplace, and their legal status, their U.S. government property, makes private sales problematic. These stories underscore how easily even extraordinary artifacts can slide into ordinary neglect. Something that once required titanic effort to obtain a rock chipped from a valley on the moon can end up forgotten among boxes and tools, its cosmic significance obscured by dust. The moon has mountains, taller than the Rockies. At a glance, the moon looks like a relatively flat disk with craters. but its surface includes towering mountain ranges that rival or exceed many of Earth's famous peaks. These mountains didn't grow from colliding tectonic plates like the Himalayas or Rockies. They were blasted into being by impacts. When a giant asteroid or planetesimal struck the early moon, it excavated huge basins. The energy of the impact sent shockwaves rippling through the crust, piling up rocks at the rim and beyond. Those uplifted, fractured rims became mountain chains. Montes Apenninus, along the edge of the Imbrium Basin, rises sharply from the lunar plains, with peaks reaching roughly 5,000 meters above the surrounding surface, comparable to or higher than many Rocky Mountain summits. Mons Huygens, often cited as the tallest lunar mountain, stands about 5.5 kilometers above adjacent terrain. Near the Apollo 15 landing site, Mons Hadley looms roughly 4.5 kilometers high. Astronauts described it as a massive wall of rock dominating the horizon. Because the moon lacks atmosphere and haze, distant mountains appear crisp and close, making their scale tricky to judge by eye. Climbing such peaks would be different from mountaineering on Earth. Lower gravity would make hauling gear easier, and there'd be no altitude sickness from thin air. But the vacuum, radiation, and dust would add their own hazards. One day, human explorers might trek along those ridges, standing on summits blasted into existence by unimaginably violent impacts long before Earth had continents in their present form. It's covered in ancient lava seas called Maria. The dark patches that give the moon its familiar face are not seas of water, but seas of ancient lava. Early telescopic observers named them Maria, singular, mare, thinking they were oceans. We now know they're vast basalt plains, the frozen surfaces of immense lava flows that filled giant impact basins. After massive impacts created depressions in the moon's crust, the still hot interior responded. Magma welled up through fractures, flooding the basins with molten rock. Over time, these lava lakes cooled and solidified into smooth, dark basalt. Subsequent smaller impacts peppered them with craters, but the overall plains remained relatively flat compared to the surrounding highlands. Major Maria include Mare Imbrium, Sea of Rains, Mare Serenitatis, Sea of Serenity, Mare Tranquillitatis, Sea of Tranquility, where Apollo 11 landed, Mare Crisium, Sea of Crises, and Oceanus Procellarum, Ocean of Storms. Despite their watery names, they are dry rock. Maria basalt is denser and richer in iron and titanium than the anorthositic rocks of the highlands, which is part of why these regions appear darker. They absorb more sunlight. They also helped create some of the moon's gravity mascons. Interestingly, most Maria lie on the near side. The far side has far fewer large volcanic plains. That asymmetry ties back into the mystery of why the moon's crust is thinner and more volcanic on the side facing Earth. From our perspective, the dark Maria have defined the moon's appearance, and by extension, its presence in art, myth, and navigation, for as long as humans have been looking up. NASA left retroreflectors on the moon, and they're still working. Scattered on the moon are a handful of deceptively simple devices that have quietly been making some of the most precise measurements in space science for over 50 years. Laser retroreflectors. Apollo missions 11, 14, and 15 left them on the surface, and 2 Soviet Lunokhod rovers carried similar arrays. Each retroreflector consists of an array of corner cube prism special mirrors that reflect incoming light directly back to its source, regardless of the angle. From observatories on Earth, scientists fire powerful laser pulses at these arrays. A tiny fraction of the photons hit the reflectors in return. By measuring the round-trip travel time of the light to picosecond precision, they can determine the Earth-Moon distance to within millimeters. These measurements have enabled a wealth of science. They've confirmed that the moon is receding at about 3.8 centimeters per year. They've been used to test Einstein's general relativity with high precision by checking, for example, how gravity affects the Earth-Moon distance over time, and how the system responds to the sun's gravitational field. They've helped refine our understanding of the moon's interior by tracking tiny variations in its orbit and physical libration. Despite enduring extreme temperature swings, micrometeoroid bombardment, and decades of dust deposition, the retroreflectors still work. Their efficiency has declined somewhat, likely due to dust and thermal effects, but they continue to send back enough photons for useful measurements. As new landers head to the moon, some plan to carry upgraded retroreflectors, expanding the network. These silent, passive instruments are among the most enduring legacies of the first age of lunar exploration ongoing experiments that keep telling us in exquisite detail how our nearest neighbor is moving. The moon has an official peace treaty governing its use. While the moon itself is airless and lifeless, human activity around it is governed by laws and agreements. The most important is the 1967 Outer Space Treaty, formerly the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the moon and other celestial bodies. Key provisions of the treaty include: space, including the moon, cannot be claimed by any nation. No country can declare sovereignty over lunar territory. The moon must be used for peaceful purposes. The placement of nuclear weapons or other weapons of mass destruction in space or on celestial bodies is prohibited. States are responsible for national space activities, whether conducted by governments or private entities. They are liable for damage caused by their space objects. Countries should avoid harmful contamination of celestial bodies and adverse changes in the environment of Earth from bringing back extraterrestrial matter. Later, the 1979 Moon Agreement attempted to go further, framing the moon and its resources as the common heritage of mankind and calling for an international regime to govern resource exploitation. But major spacefaring nations, including the US, Russia, and China, did not ratify it. As a result, the Outer Space Treaty remains the primary legal framework. More recently, the Artemis Accords, a set of non-binding principles spearheaded by the US, have gathered signatories who agree on guidelines for transparency, interoperability, protection of heritage sites, and the concept of safety zones around lunar activities. Russia and China have declined to join, pursuing their own joint international lunar research station concept. As lunar activity ramps up with plans for mining ice, building bases, and operating commercial services, the legal gray areas around ownership of extracted resources, access rights, and conflict prevention are coming into focus. The existing treaties enshrine high-level principles, but leave many practical questions open. In that sense, the moon has a peace framework, but one that will be stress-tested in the coming decades. The moon's shape isn't perfectly round. It's lopsided. The moon looks like a perfect sphere from afar. In reality, it's somewhat squashed and lopsided. Its shape and mass distribution have been sculpted by tides, impacts, and internal processes. Gravitationally, the moon's center of mass is offset by about 2 kilometers toward Earth relative to its geometric center. Combined with the near side-far side crustal differences in maskins, this makes the moon's interior asymmetrical. Those imbalances helped lock the moon into its current orientation, with the heavier, thinner, near side facing Earth. Physically, the moon is slightly elongated in the Earth-facing direction, stretched by tidal forces early in its history, when it was molten and closer. That elongated shape has since cooled and solidified. It's also slightly flattened at the poles, like most rotating bodies, though the effect is subtle compared to Earth's equatorial bulge. These deviations from a perfect sphere don't change its appearance much to the naked eye, but they matter for orbital dynamics, tidal interactions, and long-term stability. They also encode a record of ancient conditions: how fast the moon once rotated, how close it was to Earth, and how its interior cooled and rearranged. Some Apollo missions may have brought Earth microbes to the moon. Before Apollo 11, one of NASA's worries was backward contamination, the possibility that lunar material might harbor life harmful to Earth. Astronauts were quarantined after their missions, and lunar samples were handled under strict isolation. Less attention was paid to the opposite problem: forward contamination carrying Earth life to the moon. Spacecraft and suits were cleaned and baked, but by modern standards, they weren't fully sterilized. It's almost certain that some hardy microbes hitched rides on Apollo hardware. Most would have died quickly in the vacuum, radiation, and temperature extremes, but a few anecdotal cases raised eyebrows. The most famous involves Surveyor 3, an unmanned lander that touched down in 1967. In 1969, Apollo 12 astronauts visited it, removed parts, and brought them back. Later laboratory analysis reportedly found viable bacteria, Streptococcus mitis, on a piece of foam from the camera. This was initially heralded as evidence that Earth microbes survived 2 years on the Moon. Later reviews, however, strongly suggested the contamination occurred on Earth during handling. The lab environment at the time was not as controlled as it should have been. Even if that case doesn't hold up, experiments on the International Space Station have shown that some microbes and spores can survive in space for extended periods if shielded. That raises the possibility that a few terrestrial microbes might still lurk in sheltered niches on Apollo hardware or in buried waste. Today, planetary protection guidelines are stricter. For Mars and other potentially habitable worlds, great care is taken to minimize forward contamination. The Moon, considered less of an astrobiological concern, has looser rules. But as we plan for longer stays and more intensive activity, the question remains, how clean should we keep the Moon? And how might our biological footprint complicate future searches for truly indigenous life elsewhere? We've only explored a tiny fraction of the lunar surface. Given how often the Moon appears in our night sky and in our scientific history, it's easy to assume we've explored it thoroughly. In reality, the areas that humans and rovers have physically visited are minuscule compared to its total surface. The Moon's surface area is about 38 million square kilometers, roughly equivalent to the continent of Africa. The 6 Apollo landing sites, plus Soviet and Chinese landers and rovers, cover only tiny patches. The total distance driven by all lunar rovers combined is less than 70 kilometers. Astronauts have walked a few dozen kilometers in total. If you colored in all the traverses and landing zones on a lunar map, they'd barely be pinpricks. Orbiters have mapped the surface in great detail: topography, composition, gravity, temperature. But maps are not the same as samples. We've only physically collected rocks from 9 near-side locations, all within a relatively narrow equatorial belt. Lunar meteorites broaden our reach slightly, but we often don't know exactly where on the Moon they came from. That means vast regions remain unsampled. Most of the far side, the poles, many basins and highlands, and all the suspected lava tubes. Important questions about the Moon's internal structure, volcanic history, and resource distribution can't be fully answered until we go to more places, dig deeper, and stay longer. Moon missions left more than 400,000 pounds of trash. Every mission to the Moon that lands something leaves something behind. Descent stages, rovers, scientific instruments, flags, tools, cameras, insulation, forgotten hand tools, even bags of human waste. Over the decades, this has added up to a surprising amount of material, roughly 180,000 kilograms, or over 400,000 pounds. Some of this is intentional and functional: seismometers, retroreflectors, experiment packages. Some was left for weight reasons: empty fuel tanks, spare equipment, and any mass that wasn't worth hauling back off the lunar surface. Some is accidental: crashed probes, failed landers, impact stages aimed deliberately at the surface for seismic studies. There are also more symbolic items: a tiny aluminum figure commemorating fallen astronauts and cosmonauts, golf balls hit by Alan Shepard, commemorative plaques, mission patches. On a world with no wind or rain, all of it will remain for millions of years, gradually buried by slow-falling dust and micrometeoroid gardening, but not erased. As more missions arrive, governmental and commercial, the amount of hardware and debris will grow. Some have called for protecting Apollo sites and other historic areas as extraterrestrial heritage zones. Others imagine future scavengers repurposing old landers and rovers as raw material. The Moon, for better or worse, is becoming not just a destination, but also a dumping ground. One day, Earth's rotation may lock to the Moon. We've already seen that the Moon is tidally locked to Earth, one rotation per orbit. Over vast timescales, tidal friction is also slowing Earth's rotation and pushing the Moon outward. If nothing else intervenes, no solar expansion, no major gravitational perturbations, Earth could eventually also become tidally locked to the Moon. In that far future state, a day on Earth would equal a lunar month. and one hemisphere of Earth would always face the moon, while the other would never see it. In such a world, the dynamics of tides, climate, and even day-night cycles would be radically different. But this scenario is largely theoretical, because the sun's evolution will likely disrupt the Earth-Moon system first. In a few billion years, as the sun swells into a red giant, Earth may be engulfed or its orbit significantly altered. The delicate slow dance between Earth and Moon won't play out to completion. The Moon could be humanity's first off-world colony. Despite all the challenges, radiation, dust, cold, cost, the Moon remains the most plausible location for humanity's first true settlement beyond Earth. It's close enough for relatively quick travel and communication. It has resources, water ice, metals, silicates, and abundant sunlight at some polar ridges. It offers a testbed for technologies and social systems we'll need if we ever aim to live on Mars or beyond. NASA's Artemis program envisions a sustained human presence near the lunar South Pole, supported by the Gateway Station in lunar orbit and a network of landers and surface systems. China and its partners are planning their own international lunar research station, also targeting polar regions. Private companies are working on cargo landers, habitats, and in situ resource utilization (ISRU) technologies. A lunar colony won't look like a science fiction city of glass domes. Not at first. It will probably begin as a small cluster of pressurized modules, maybe buried under regolith for protection, with careful recycling of water and air. Power will come from solar arrays or small nuclear units. Rovers, robots, and maybe one-day vehicles traveling through lava tubes will extend human reach. If it succeeds, the Moon could become a logistics hub, a place to fuel deep space missions, assemble large structures, test closed-loop life support, and manufacture certain materials. It could also be a place people are born, grow up, and live lives that are truly off-world. The Moon is slowly becoming a hub for global space politics. As more nations and companies focus on the Moon, it's becoming a stage for geopolitical competition and cooperation. Who gets to mine ice in a particular crater? How close is too close for one base to be to another? How are scientific findings and resources shared? These questions are no longer speculative. The Artemis Accords represent one attempt to shape norms: transparency, deconfliction, open data, protection of heritage sites. China and Russia's lunar plans represent another block, with their own priorities and standards. Smaller nations are choosing partners, contributing instruments, or planning their own landers. Private entities are negotiating contracts, rights, and responsibilities. The Moon is thus becoming a mirror for Earth's politics. It could become a model of shared, peaceful development or another zone of rivalry and tension. The treaties we already have, and those we develop in the coming years, will set precedents for how we approach Mars, asteroids, and other worlds. In the end, the Moon is more than a rock. It's a recorder of our past, a driver of our present, and a laboratory and arena for our future. It holds the scars of the early solar system, stabilizes Earth's tilt, shapes tides and time, and now, increasingly, reflects our ambitions and choices as a species.